So what you need is some algorithm that's going to home in on the good collections of settings, because in this big space of, this knob could be at a 10, this one could be at a 3, or this one could be at a 7, and so on. In this big space of possible settings, there are going to be some regions that are going to work pretty well, right? And so you need an algorithm that's going to home in on them. So basically, I think what Eliezer did is he took the environment that he saw around himself and he projected that forward. And so he thought this was going to cause basically the end of the world. And it turns out that big thesis is wrong, right? And it's wrong precisely because we didn't get strong systems before we got systems that could understand human values. If you have an AI and it has its own network and you just give it its own network weights, you say, okay, which weight should you change? Well, it doesn't know, right? Because the thing's a black box. The thing is it's a black box to us. It's also a black box to itself.
Roko, it is so surreal getting to talk to you today. I've been trying to search for the right analogy. It feels almost like meeting a cryptid, getting to talk with one of my favorite mythological beings, just because your name, in a way that not even Nick Bostrom with simulation theory or any of the other thinkers in the AI space can really claim, your name has been associated specifically the idea of AI alignment, of human displacement through some kind of technological revolution that we are all seeing unfold. I just wanted to ask, from your perspective, what has your direct association in normal everyday life? Is that your affiliation with the Basilisk something you come into contact with? Is it something you think about regularly?
Well, not so. Funnily enough, where I am, in England, it's not that big. If I'm in California, because I visit California, I visit the Bay Area quite a lot, it becomes a little bit more prominent. But I have been to one event where I introduced myself as Roko, and somebody said, "Oh my God, that's really crazy. Have you heard of this thing called Roko's Basilisk?" And I was like, "That really happened. That really happened." Yeah, probably going to happen a few times, a few more times moving forward. But because this stuff really happened. A lot of the AI theorizing that dominates the discussions nowadays came from a long forgotten era of the 2000s. I invented the Basilisk in the late 2000s and 2009, and it was sort of forgotten, really quite seriously forgotten for quite a long time. Now that things are sort of starting to move, because basically in that time period, right, in the 2000s and the very early 2010s, there are a very small number of people who were really thinking very seriously about artificial intelligence. And I basically knew all of them personally. I mean, I personally knew Shane Legg, for example, who's the DeepMind co-founder, right? And I knew Nick Bostrom, and I knew Eliezer. I knew a lot of these people. I even had emails with some of the old school AI people. I emailed with Marvin Minsky, right? And
Wow.
I knew Hofstadter. So a lot of these people in that era. Oh, and Schmidhuber, I got a PhD with Jürgen Schmidhuber, which I then turned down because I was worried about AI risk. So a lot of these people were in a fairly tight-knit community back in the 2000s. Between sort of about 2010 and 2015-ish, we were still in this period of nobody really had any idea when we were going to get AI. And a lot of people thought we were never going to get it, right? Which is pretty crazy to think about it. There was a whole period after a lot of this stuff was kind of already written, already decided, a lot of it already laid out, where it was a big mystery. It could be in 5 years, which it turned out was basically what happened, or it could be 150 years. I mean, it's not completely crazy to think from the point of view of 2005, well, maybe we will get human level AI in 150 years. And people like David Chalmers, who wrote a piece on the future of artificial intelligence, said something like, it could be a decade, it could be a couple of centuries, but it's probably going to happen, right? And it turned out it was more like a decade. So it is a bit crazy that basically a lot of that stuff happened in a period when the technology wasn't ready. And to some extent, that's because the technology surprised a lot of people, including me, that basically you could just build a language model, and that would, just keep making a language model bigger. Because I worked on language models before LLMs were a thing. So I had a job in a company where we were doing machine translation, And one of my jobs was to work on these language models. But you see, the thing is, these were not huge neural network. Well, some of them were neural network based, but they weren't huge, right? So they were relatively simplistic, right? They would literally be able to predict if you said the cat sat on the, and then the next word would be matched with high probability, right? So the idea of a language model, of things like n-gram language models, is kind of an old idea. And the idea that, the idea that the key to artificial general intelligence was like just language models was absolutely mind-blowing, right? If you'd gone back to 2010 and said to people, yeah, those like n-gram language models that you have as like an exercise for students in the back of the AI textbooks, yeah, that's it. It's just that. There's nothing mysterious. Just build a really big, really good model of language, and then you just put this little teensy bit of reinforcement learning on it to make it into a helpful assistant, and you're good to go.
So what if you could go back in time and give a single piece of information to those people to help them reframe why that was successful? Is there anything that sticks out?
Yeah, basically read Richard Sutton's Bitter Lesson and really internalize it. I think if you'd really internalized the Bitter Lesson, it would have been fairly clear that something like that was going to happen. And it was
Hmm.
also sort of unclear to people that neural networks were actually going to work. I mean, I'd looked at neural networks, but again, when neural networks are relatively small and you don't have that much compute to train them with, they're not very impressive. They're relatively inefficient at small scale compared to other machine learning models. So a lot of people, there's like a whole bunch of machine learning theory, statistical learning theory, VC dimension, all of this kind of stuff, right? And all of this stuff basically told you why neural networks wouldn't work, right? And you had things like, overfitting and stuff like that. And you said, well, it won't work because, there's so many parameters, it's going to overfit the data, it's not going to learn, all of these is going to find like a local minimum rather than a global minimum of the cost function. And all of this stuff, it
Mhm.
turns out, was misleading, right? It was leading you the wrong way. And it turned out that neural networks were in fact really quite good at, you know, becoming good language models, which in hindsight shouldn't be that surprising given that we are neural networks that use language, right? So it shouldn't have been that surprising, but it was. And I think some of the sort of philosophical, almost theological sort of debates
Hmm.
about the nature of intelligence really led people astray. And if you just sort of ignored all of that, or even just better still, just pretends it didn't exist, and you're just very empirical about it and said, okay, what do we want? We want an AI system that can talk to people. And what fundamental idea, is most important? Well, it's this bitter lesson thing that basically the more you can remove, the less you understand about how your AI works, the better, effectively, right? You don't really want to understand how it works. You just want to cram in a bunch of data and have the simplest possible machine, like a sort of sausage maker. When you put all the bits of
Hmm.
gristle and meat into it and you turn the handle and the sausage comes out. You just want to build the simplest possible sausage making machine for all of this data and spit something out. If you'd had that idea, you may have come to neural networks as being the thing that was going to actually work. Although, I mean, I did some AI research at Edinburgh University, and my idea was basically I thought it was going to be Bayesian non-parametrics because they're sort of more theoretically justified. But it turns out
Hmm.
Bayesian non-parametrics complete complete bust, didn't work, complete disaster. Maybe it could be made to work, but that's just not the way things turned out. So it turned out that neural networks and stochastic gradient descent was excellent, and things like Bayesian non-parametrics and Markov chain Monte Carlo just didn't work. But so there was a certain amount of like luck of the draw of like which technical paradigm does actually work. Um, but certainly the idea of being empirical and realizing, in a way, demystifying intelligence by just realizing that, look, all intelligence really is a function. That's all it is. It's like, when you were in grade school, you probably learned y equals x squared, right? Everyone remembers that.
Hmm.
Or at least maybe they have
Yeah.
nightmares about it. That's all intelligence. All intelligence is a function. It's just a function. It's like y equals x squared. It's just X is a bit bigger and more complicated and Y is a bit bigger and more complicated. But basically that's all it is. And then the question is, how do you pick out the right function that's going to be able to hold a conversation with people where, X is
Mm.
the conversation input and Y is the conversation output. And, it turns out that neural networks and stochastic gradient descent are a pretty good way of doing that. So it's kind of bizarre how all of this stuff has fallen into place relatively quickly and in quite a surprising way. But a lot of the theory of stuff like AI alignment and AI safety and the Basilisk and all of this stuff, it all happened before we knew how AI was actually going to be realized.
Yeah, and as far as the development path, it feels like we can be a little bit charitable to the experts because around the invention of the perceptron, there were so many grand promises made, and people did assume that the uh, scaling up of those systems would be so relatively straightforward that they were already prognosticating about AI as a solution to basically every problem under the sun,
Well,
right? And
so
when that dream collapsed,
Kurzweil was kind of doing this, and at the time, people made
yeah.
fun of Ray Kurzweil for his graphs, where he has this really cool graph where it's basically like you have this increasing super exponential trend of compute, and you have like an ant and a mouse and a monkey and a human and then the whole of humanity, and he just like sort of basically draws this graph kind of by vibes and says, and therefore the singularity is going to happen in 2045. And people were lampooning him. They're like, this is crazy. This is basically numerology. The rapture of the nerds is what they
Mm.
called it. And it turns out that Kurzweil's approach was pretty good, actually. I mean, it wasn't perfect. It didn't really get everything. When you look at the specifics of his predictions, they tend to be off. But the general gist of it is basically great, right? And you got to remember at the time in the 2000s,
Yeah.
people didn't think that AI would ever happen. So the most common sense, normal person opinion was that AI only belonged in sci-fi books. And the sort of educated academic, David Chalmers types were saying like, well, it could be a couple of decades, it could be a couple of centuries, but it's probably eventually going to happen. Although even to say that was kind of controversial, right? Because there were other people who
Mm.
would say human intellect is somehow magical and divine, and there are a bunch of people who went absolutely nuts about Gödel's incompleteness theorem and said because of Gödel's incompleteness theorem, an AI can never truly be intelligent, only a human can. And it turns out this was all just complete nonsense because they didn't understand Gödel's theorem and, they didn't understand that, computers, that human brains aren't actually true and complete anyway, and like a bunch of other problems, right? So, just the idea that we were going to get AI at some point was revolutionary. And the fact that we got it so quickly was pretty crazy. I personally thought that it would take a little bit longer. I was thinking
Mm.
more like, we're going to see some real progress in the 2030s and 2040s. I didn't expect it to happen so soon, but it turns out we really were right on the cusp of the technology being invented at that point in time. We were just at the precipice of it being. It was just about out of reach in 2010 when I was doing AI research, but not quite.
Well, and from what I understand of the Eliezer or Ilya Sikowski's uh, work, even he and his mentor, not Sutton, I'm blanking on the name, the godfather of AI, Hinton,
Hinton.
were derided, relatively mocked for their continued insistence, right? It wasn't until the ImageNet breakthrough,
Yeah.
I think, that they were really given
Yeah.
shrift. Is that when you reevaluated that, or when did
Well,
that
I
change
so
happen for you?
I was working on what was called the semantic web at Edinburgh University, which was an attempt to
Hmm.
basically use types of logic to build artificial intelligence. So it was a sort of rebirth of the old logic-based AI. And I spent about 6 months working on this until I sort of convinced myself that it couldn't work. And my
Hmm.
supervisor at the time was Professor Alan Bundy. And I distinctly remember going to him in a meeting, in a supervision meeting. I said, look, Alan, it's not going to work. You can't build AI, you can't build useful web agents on the basis of first order logic. And this is why. It's because
Hmm.
first order logic has these things called models from model theory that bear absolutely no relation to the real world. And because they bear no relation to the real world, the logic that governs them isn't going to behave in a way that's isomorphic to how things work in the real world. So it'll never work. And all of this stuff
Hmm.
is nonsense. And his answer to that, which I kind of pisses me off still, was that like, well, whether you're right or wrong, I can't switch to working on a machine learning based approach because, I wouldn't get funding for it because I have a reputation in logic. So
Wow.
we're just going to have to keep on working on this. And so for that reason, I actually quit. So I was in a PhD program with him, and I quit with just a master's degree for that reason, because he didn't want to switch to machine learning. But at the time, I was sort of more enthralled with Bayesian non-parametric approaches, because they're sort of more mathematically elegant. But it just turns out that mathematical elegance is not at the moment much of a bonus. What you really need to make AI work well in practice is just an absolute metric ton of data, right? So when you try and make a mathematically elegant model, you typically make some sacrifices on what it can do and what it can learn and what it can ingest in order to make all of the nice mathy stuff work. Um, but you
Hmm.
don't really want to do that. You just want to sort of throw everything but the kitchen sink into it, maybe even everything, including the kitchen sink. And that's that's basically why Sam Altman is such a genius. He had the idea, which nobody else really had, of like, well, why don't we just make it bigger, right? And in 2016 or 2017, that was actually that was actually kind of radical, right? And a lot of the sort of failure of artificial intelligence to progress between about 1970-ish and 2010-ish stems from the fact that in the sort of 70s, people were very excited about AI because there
Hmm.
was a very strong theoretical philosophical case that you could make a synthetic intellect that could replace a human worker. And so people tried a bunch of stuff, right? They tried, first order logic. They tried, planning algorithms, and that line of research led us to things like databases and chess playing AIs, right? So that's not nothing, right? I mean, databases are kind of a big deal, right? It also led to a lot of logic programming languages, Prolog, stuff like that. So it was kind of a big deal, but basically didn't work, right? And the reason it didn't work is what I sort of worked out, which is that logic-based AI won't work because model theory doesn't actually reflect reality, right? That models of first-order logic they're very strange. They don't bear much relation to the world we live in, and it's sort of almost quite. It's like and it's almost like a coincidence that this even works at all for things like
Hmm.
counting rocks. But it turns out that there's like a pretty strong isomorphism between like sets of rocks and sets of numbers, right? So if you have a set of 5 rocks and a set of 3 rocks and you combine them, you get a set of 8 rocks. That's actually quite solid, right? But once you go to things like properties and you know um uh properties of objects like predicates, that kind of thing, it really breaks, right? Predicates in real life do not work how predicates work in logic. When you say for all, that doesn't really mean for all. When you say there exists, that doesn't really mean necessarily that there exists. It's all a bit different. So
Interesting.
yeah, I mean, people in the 1970s were pretty enthusiastic about it, so they got a lot of money, right? And then it didn't work, right? And so because it didn't work, over time, AI as a field became less and less and less reputable, and they got less and less money. But at the same time as these AI researchers were getting less and less money, right, the amount of compute you could buy per dollar went up. So you can imagine this situation where a researcher in the late 70s might spend like, $10 million on his compute. And then a researcher in the 80s might spend $1 million. And then by the 90s, the grants are dried up and you only get $100,000, right? And so basically, these poor researchers were working with basically a fixed amount of compute for a very long time, right? And then until the
Hmm.
2000s, where it's like, fuck you, AI researcher. You don't get any compute. If it doesn't work on your laptop, you can't have it. Okay. So in the 2000s, these guys are literally working on their laptops, right? And of course, that laptop is as powerful as the $10 million computer from the 1970s, but the poor guy still doesn't have any more compute, right? And then suddenly, like GPUs became a thing, and people realized that you could
Hmm.
use so GPUs, graphics processing units, were used for playing computer games, right?
Yeah.
I mean, I know some younger people might not realize that, right? But GPUs were actually not invented for AI. Right? Nvidia is not an AI company; it's a computer games company that sort of suddenly
Yeah.
found its like second calling in life. So people invented GPUs to play computer games. If there hadn't been computer games, we might never get AI. right? That's absolutely mind-blowing, right? Because I don't think with the way that Dennard scaling and increasing clock speeds ended around about 2003 or something, if computer games hadn't been a thing, there probably wouldn't have been much of an economic forcing function to make computers more powerful, at least not, really try really hard at it. Maybe people would have tried a little bit, but not very much. And so I can imagine this world in which guys just like go out and meet girls and play sports and are all manly, and there aren't any nerdy guys who want to play computer games, in which we're sort of stuck on planet Earth forever because we never invent artificial intelligence. But it turns out, no, at exactly that point in time, just when we needed it, we invented GPUs, and some people discovered that it turns out this is a sort of mathematical coincidence. The kind of mathematics you need to project a three-dimensional scene onto a two-dimensional like camera can be very easily repurposed to do back propagation for neural networks, right? It's this
Mm.
crazy coincidence that it's basically the same math. It's just matrix maths, you see, right? So matrices are useful for converting, for doing like rotations and projections in space, right? But it turns out you can also use matrix math to do back propagation and to do the gradient updates um, in neural networks, right? Where you're basic. So just to explain for people who don't know what back propagation basically is, imagine you agree with me, or you agree with Richard Sutton that AI is basically a black box function. It's like y equals x squared, except it's a complicated function. It's not like the squared function. It's like some function with like many, many, many little knobs and switches and twiddles on it, right? And you have to get all of these knobs
Mm.
and switches and twiddles just right for the thing to actually be intelligent, right? So you want to optimize, you want to choose which collection of settings on all those little knobs and dials and stuff is correct, right? Well, one way you could do it is you could just try all of the possibilities, but you can't do that because if there's like a billion different knobs and they each have like 1,000 different settings, right? The number of different possibilities is going to be 1,000 to the billionth power, which is incredible, far, far larger than the number of atoms in the universe. You can't try every possibility. Well, another one is you could just try some at random. So you randomly sample, right? But the problem is in your huge space of possibilities, if you just randomly pick points in this, what we call parameter space, right, you'll never get anywhere near the right ones. It'll just never work. So what you need is some
Mm.
algorithm that's going to home in on the good collections of settings, because in this big space of this knob could be at a 10 and this one could be at a 3 or this one could be at a 7 and so on, in this big space of possible settings there are going to be some regions that are going to work pretty well, right? And so you need an algorithm that's going to home in on them. And so, as I said, the obvious way is like, well, I'll try every possibility or I'll try them at random. Another one is I'll do evolution. So you try a bunch of them at random and see how well they work. And then the ones that
Yeah.
do better, you keep those and you kill off the ones that don't do as well. And the ones that you do better, you sort of like mate them, you reproduce them. So you produce new parameter settings that are close to them that represent their children. And then you try out those children as well. So that would be called a particle swarm optimizer, right? Now, this sort of particle swarm or evolutionary optimization is what created us, right? We were created by that kind of optimization. Or at least, living things were. But it turns out it's not very efficient, right? If you have like a whole planet and you have, um, trillions of bacteria over billions of years, yes, you can get particle swarm optimization to work, but it's not great. And the reason it's not great is because if you have a high dimensional parameter space and you have a successful entity and you want to make it have children and evaluate how good those children are, well, if there's like 1,000 different settings for each knob, right? And maybe you just want to change just one or two knobs together to get the right fix, even if it's just two, if there's 1,000 different knobs and you need the right setting on two of them, that's 1,000 times 1,000. That's 1,000,000 different children that entity would have to fully populate the sphere of possibilities around it, right? At distance two. And so that's kind of hard to do, right? So your optimization runs very slowly. Most of the children are mutants who don't work very well, right? Very, very few.
Malformed.
There's a
Yeah.
yeah, very, yeah, they're, yeah, they're like wokes. Basically, like what
Interesting
happens
corollary there, yeah.
what happens with this particle swarm optimization is it's too slow, right? It doesn't home in on the right direction because it's kind of like a blind optimizer, right? It can't see, well,
Mm.
which direction is actually working, right? Do I need to twiddle the A knob or the Z knob or whatever, right? It doesn't know, so it just produces one child with the A knob turned up and one with the M knob turned down, and so on and so forth. It's just shooting in the dark. So gradient-based optimization is a very clever idea that instead of just trying to twiddle every parameter all at once and see what happens, you pick one single parameter at a time, one single knob, right? And you basically turn it incrementally a tiny amount, kind of like if you're in a bathroom and you have like, so in the UK we have two separate taps, one for hot, one for cold, right? So suppose you had these taps and you actually didn't know which one was hot and which one was cold, and you had the water pouring and you don't want to burn yourself, right? Or if you're in America, you have like a heat setting, right? You have one for flow, one for heat, and well,
Yeah.
you know which one is for, you know which one's for flow, so you know which is the heat knob, but you don't know which direction is hotter or colder because somebody rubbed off the markings, right? So instead of just turning it all the way to hot and burning yourself, or all the way to cold and having an accidental cold shower, you just turn it incrementally, just a little bit, right? You've done this, right?
Yeah, of
Yeah,
course.
you just turn it
Temperature
just
testing. Yeah.
a little bit, a tiny little amount, and you see whether it got warmer or colder. And if it did get warmer, oh, well, I'll keep turning in that direction then, right? So that is how gradient descent works. It looks at one parameter only at once, and sees what the effect of turning that parameter just a little bit is on the final output. And believe it or not, that actually works, right? And even more interestingly, the process to do that is basically based on matrix math. So you do a bunch of these matrix calculations, because the reason you do matrix calculations to twiddle the knobs on your network is because each of these parameters will go through, like if it's a parameter in the 7th layer, right? Or let's say it's the 7th layer out of 10, right? There's still 3 layers until you get to the output from that knob, right? So if you twiddle that knob a little
Yeah.
bit, you have to calculate the consequences of that all the way to the end. And what you actually, so you know the way, the magic of gradient descent is instead of actually, because again, if you actually twiddled every single knob in the network, every single update step, right, it would be too computationally expensive. Because let's say you have a billion parameters and you want to run a trillion, a billion steps, right? You're multiplying together, right? It doesn't work. So you need to reuse part of that calculation. And the way you do this is you work out the gradients going backwards through the network, right? Rather than working out the consequences of each twiddling going forwards, you actually find this neural network is a differentiable function, and you can take its derivative like you could in calculus at high school, where you say, dy by d, if y equals x squared, dy by dx equals 2x, right? It's exactly that. You just propagate this gradient backwards through the network. And the way that you do that is with a series of matrix multiplications. So each matrix multiplication is propagating the gradient one layer back in the network. And that is why this whole thing worked out. That piece of maths is why we have AI. And it's why we could use these GPUs that were made for playing computer games, where the matrix maths is for projecting a 3-dimensional scene onto 2 dimensions and working out, if there's a bad guy there and there's a tree there, does the tree cover the bad guy? Do I have to paint that his pixels on the screen or not? Right? The way you work that out is with matrix math, but the same matrix math can be used to propagate backwards the gradients of effects of twiddling each knob on the network. And that is basically how neural networks learn. So obviously that's been known for a long time. Like that is from the 60s, that's old technology. But the magic was having GPUs, graphics processing units, that could do this incredibly fast. Because you try and do matrix maths on a central processing unit, on a CPU, it just goes and it does, well, here's the first element of this matrix, I'm going to multiply it by this one, and that's really slow, right? Because you're doing each one at a time. But graphics processing units, they have these thing called stream processors. They basically have a special purpose processor that multiplies millions of numbers all at once in parallel, right? And that's the difference between, GPU based computing and CPU based computing. In a CPU, in a central processor, when you run a normal program like a Python program or a C program or the code for, this application we're using. It's always sequential processing of instructions. You start the program, you start a for loop, you start a while loop, then you look at what's next, then you look at what's next. It's all sequential because the next step could be anything. You could do anything. You go back, you could exit, you could whatever. But in a GPU, it's always the same thing. It's always just multiply the next numbers. And because there's no dependency of the next computation on what you did in the previous one, you just do it all in parallel. So you do a million computations all at once. You multiply a whole massive matrix all at once. And that effectively is one step of, or one layer of one step of learning in the neural network. So that is the magic that happened, basically, that to get us to where we are today.
It is magical. I also remember hearing an anecdote. I think Jeff Hinton said when he was at Google that what if instead of killing off the poorly performing instantiations, we just tell them what they did wrong. And that is the
Kind of, yeah.
backpropagation that
Kind
you're
of, yeah,
referencing
yeah.
there?
Yeah, but basically, yeah. And because you're telling it what it did wrong, you don't actually have to have multiple instantiations. You just have one set of weights and you just update it. Whereas in evolution, you can't just have one, creature, one pigeon. You have like a million of them, and some of them die, and some of them have more babies and so on, right? But so that's particle swarm optimization, because you have a swarm of particles, right? But with modern AI, you're doing back propagation. So you're, as you say, you're finding, in which differential direction, in which like little tiny sort of step is the next step that you need to go, and you send it in that direction, and then you recompute. A lot of the discussions that people had in the 2000s about AI and AI risk have now become quite live, effectively, because it seems that we are going, we kind of have human level AI mostly. I mean, it's not, there's some ways in which it's defective, but we mostly have it now. And people are thinking about what the consequences of that are going to be. Is it going to be good or bad for humanity, etc.?
As someone who does not have your technical background or grasp of the specific mathematics, I try to think of it in terms of analogies. One of the interesting things you said there to me was that it's crazy that this capability came through games. And a historical analogy, I wonder if you would agree is appropriate, is that, if you go back to ancient Mediterranean cultures and you were just asking based on first principles, who's going to be the reigning military power 100 years from now, looking at the Spartans and the Athenians, you would assume the Spartans because their military prowess was obviously leagues ahead of any of the democratic states. What did the Athenians had? They had plays, they had theater, they had simulations, games in that way. And who actually came to dominate? The Athenians, because they were able to, what is the corollary there? Adhere, they were able to project, they were able to imagine, create civilizational structures in that way.
Yeah, I don't know what really happened with all of that. I'm a bit hazy on ancient Greek history. But the thing is, with the computer gaming connection, it wasn't really the game itself that was useful. It was just the graphics processing for it, right? So, whatever the game was,
ability.
not even simulate. It's literally just projecting rays of light, right? So the whole simulation of where are the baddies and what are their strategies and all of that is completely irrelevant. The only thing that matters for a graphics card is you have a model inside the game engine that says there's a bad guy at these coordinates and there's a tree here, and there's something else, another baddie here, and there's one of your allies here, and there's a hill. So you have this, but this is a three-dimensional model that sits in the game engine, right? And the screen and your eyes are a two-dimensional projection. So you have to do some maths to work out what a scene actually looks like, right? Because if you have a hand, well, it can be here, but it could be here, and that makes it, that makes it bigger in my eyes. It makes it smaller to the camera because it's getting further away. But to my eyes, this makes the same object look bigger, and you can also rotate it, right? So when you translate and rotate an object, right, the picture that it makes on your eyes changes, and you have to do matrix maths to work that out, right? And so it's that matrix maths that was in the graphics processing units that ended up being the thing that was used to make neural networks train and do inference quickly. Because it's not just the training, because I've talked a lot about the training, it's also the inference. The inference is also quick, because the magic of neural networks is that when you do learning, you do training, it's matrix multiplications. And when you do inference, which is basically talking and thinking, it's also matrix multiplications, except in the training part, the multiplications go back through the network. That's why it's called back propagation. In the thinking part, they go forward. That's why it's called a forward pass. So inference is forwards passes, training is backwards passes. But it's the same matrix maths, right? So that's basically what happened on the technical side. But you see now on the sort of governance and alignment side, we've got to a stage where people are struggling to comprehend whether AI is in fact going to be good or bad. And Eliezer Yudkowsky recently came out with his book, which sort of outlines the Yudkowskian thesis. If anyone builds it, everyone dies. Which I
Just
think
amazing
is
statement
basically,
of faith.
I think it's basically incorrect, but I think it's incorrect for quite an interesting reason.
Please, what is that reason?
Well, basically, you know, the Yudkowskian thesis about artificial intelligence, which he came up with between 2005 and 2007-ish, was basically that he thought we were going to build AI using some kind of optimization process, but he didn't know what it was going to be. He didn't know whether it was going to be neural networks or anything. But he thought that we were going to get AI systems which were which couldn't understand human values, at least when they were relatively weak systems. So he thought we were going to get weak systems that couldn't understand human values, and then they were going to recursively self-improve to become strong systems. And they would eventually learn human values, but not until they became very strong. And so in that process of them becoming strong, they would sort of develop their own non-human values. They might love paper clips more than they love puppies, and they would turn the world into a pile of paper clips. And this was an interesting thesis for the time, right? Because if you go back to the year 2005, what do you see? What kind of AI systems do you see in the year 2005, right? You see things like Garry Kasparov's Deep Blue. IBM's Deep Blue that beat Garry Kasparov, right, in 97, I think, right? So AI became the world chess champion in 97, which was a big deal because there were people in the 60s and 70s who said it was impossible for a machine to beat a human at a board game like chess. Impossible to beat a champion, right? Which is obviously a very silly thing to say, but some people really took it seriously. And I think there was even a bet. Somebody lost money on this. Yeah. If you look at the systems that were around in 2005, what do you notice about them? They are weak systems overall, but they don't understand human values. Not weak at chess, but weak at like understanding the world, right? But they also, Deep Blue doesn't understand human values. It doesn't have a notion of moral good or human dignity or fairness or any of these things. So basically, I think what Eliezer did is he took the environment that he saw around himself and he projected that forward and said, well, if we just keep making these types of systems, and it doesn't really matter what the details are, as long as it's some kind of weak system that doesn't understand human values, and it eventually starts to recursively self-improve into a strong system that has its own unique alien values. And if that strong system at some later point in time, that strong system at some later point in time eventually finds out what human values are, it's not going to inherently value them, right? If you're brought up to love puppies and you find out about paperclips, you're not going to love paperclips. It works the other way around. If you're brought up to love paperclips and one day you find out about puppies, why are you going to care about puppies? And so he thought this was going to cause basically the end of the world. And it turns out that big thesis is wrong, right? And it's wrong precisely because we didn't get strong systems before we got systems that could understand human values. We got systems that could understand human values in the form of LLMs before we got really strong AI systems. AI systems today, like, they're kind of like human expert level at short tasks, but they're not very good at long tasks. And, you know, nobody's really managed to make a functional AI-based firm or organization where many of them cooperate together to achieve a goal. There's like a bunch of these sort of missing parts of the cognitive tool set of AIs, but it's not like they don't understand human values. You can go and ask Claude or ChatGPT, what's better, puppies or paperclips? And it will, I'm pretty reliably tell you that puppies are better, right? And it will, and you know, if you sort of quiz it on this, it'll give you the same kind of reasoning than a human will, because it turns out language model-based AI is not really that alien, right? The whole less wrong sort of crowd, the whole sort of memeplex of less wrong was really primed to expect AIs with alien values. And Eliezer wrote about this for a long time, and he made some pretty interesting arguments for it. That, you know, there's like the mind space is very big. There's lots of different possibilities. If you just pick one out at random, it's very unlikely that you're going to get one that shares human values. But you see, the thing is,
Yeah.
we didn't pick one out at random, did we? Of course, like, no, you're not going to randomly build an AI, right? You're going to build one by doing the thing which gets it the most knowledge and competence in the quickest time with the least hardware. And what's that going to be? Well, it's just going to be to copy a bunch of human content. But when you copy a bunch of human content, you also copy the values with it, right? So for a very sort of naturalistic, obvious in hindsight reason, the main Yudkowskian reason to be worried about AI risk is basically wrong. Now, what's happened after this is he's sort of come up with some copes. He's got fallbacks, right? Okay, but the fallbacks are not as good. Okay, like the idea
Yeah.
of AIs having alien values is actually a very good idea, right? But it was wrong. But the
Well, it
fallbacks that
dovetails
he's
kind of with your idea that the mathematical model would be possible, that you could find an efficient
exactly
mathematical
exactly
simplification. Yeah.
exactly. So if yes, exactly. So if you did have AIs that were based upon the same kind of math that powers chess AIs, right? Just tree
Hmm.
search or something like that.
Yeah.
Yeah, you know, this is why I was part of the Singularity Institute, aka MIRI nowadays, Eliezer's crowd, because it did seem extremely worrying in 2007 to 2010. It really did seem, or even up until 2015, it really did seem like, if you look at the things that people were working on, you look at things like DeepMind were working on, you know, DeepMind AlphaGo, that was absolutely terrifying, because AlphaGo and AlphaZero were exactly the kinds of things that fit in with the Yudkowskian risk thesis. Because basically,
Yeah.
what is AlphaZero? It's a reinforcement-based learning algorithm which just kind of like autonomously learns how to manipulate the universe.
Mm.
And it works pretty well on pretty much any, you know, Nintendo game or Atari game, that kind of thing, right? If you got that to work in the real world, it would exactly be the paperclip maximizer. So that was
Mm.
really a terrifying time. But we got bailed out. Just, it's kind of like, you know, H.G. Wells' novel, you know, when the Martians come in and
War
try
of
to
the
destroy
Worlds.
Earth, War of
Yeah.
the Worlds, right? And
Yeah.
everyone's like, we're screwed. There's no way to recover from this. We're just going to lose. We're all dead. And then it turns out that, of course, something completely trivial kills them off. They all get like bugs or something, right? And they all, you know, die of infections because they're not used
Yeah.
to Earth bacteria. And it sort of feels a bit like that, because the you know, the thing that actually stopped the paperclip maximizer from coming into existence was the LLM, because the LLM achieves the same goals in terms of practical competence for people to do useful tasks, but it achieves them with less hardware and less computation, because instead of trying to work out how absolutely everything in the real world works, it just reads what humans have already said about it, right? It doesn't have to go out and work out every laborious little detail about the world on its own autonomously without any human input. It has sort of, instead of no human input, it's sort of like maximum human input, right? So it's almost this weird halfway house between like the logic-based approach or tree search or something like that, where you don't program the AI with any specific knowledge. You just have some general algorithm that it follows, but the
Yeah.
algorithm is sort of like a known algorithm. And then you have like this sort of like handcrafted knowledge-based type AI, like the Psych project or the Semantic Web project that I was working on. Then you have this third option, which is that you do program it with a lot of knowledge, but it's not knowledge that was handcrafted by the researchers. You just make an algorithm that's very good at ingesting text, and then you feed it all the internet text. And this sort of elegantly solves the Yudkowskian AI alignment problems, or at least some of them, because if you program it with all of this human content, it gets all of these human values, it understands all of these human concepts. Now, this is both a positive and negative because it means it learns how to be deceptive and sycophantic and lying and all of this stuff. So a lot of the bad stuff from humanity is also now being imported into AI, and now we have to use things like reinforcement learning to try and get rid of it, and that's a little bit harder. But basically,
Hmm.
the Yudkowskian thesis of alien minds has been completely and utterly blown up. And I think Eliezer still hasn't really accepted that. And you know, he sort of like published a book which is still kind of you know, it still kind of pushes this thesis, but it also, so the fallback for the Yudkowskian school now seems to be biorisk, right? So
Hmm.
you know, in his book, the big disaster is because this AI system builds a bioweapon and persuades somebody to um utilize the bioweapon to cause, you know, human extinction, right? Spoilers. um, you know, if you'd read something from Yudkowsky about 15 to 20 years ago, instead of a bioweapon, it would have been like nanotechnology. And so his traditional AI risk scenario was that there's somebody's AI model in a server in the basement, and they set it to, you know, mine Bitcoin or, you know, find the largest prime or some computational task. And as part of this, it begins to recursively self-improve. And like the Sorcerer's Apprentice, overnight, it sort of it goes from an interesting research project to superhuman level capabilities,
Yeah.
and it invents nanotechnology, and, you know, it somehow either hires somebody or bribes somebody to um to build physical manipulators for it, or you know, it just does something, and that something will then go and kill everyone in the world. Like it'll build a nano virus that goes and, you know, nanobots will go out and eat everybody or something like that. So that was the traditional risk scenario, and this is sort of there's several reasons why this is not going to happen. One of them is just that in the modern era, AI is kind of an efficient-ish market, right? So if there's some way that you could spend a relatively small amount of resources to make a superhumanly intelligent AI, well, some researcher at Facebook or Google or Anthropic or DeepMind or, you know, the Chinese one, what's it called, the one with the whale, DeepSeek, right?
DeepSeek.
Like,
Yeah.
you know, so you really think that one guy in his basement with a server working on his own or with a small team would be able to come up with an innovation that was so powerful that not only was it better than everything that all of these trillion-dollar companies can come up with, but not just better by a little bit, better by such a large amount that this thing can take over the world.
Hmm.
Right? That's not realistic. Right? Now, maybe back in 2005, it was probably a little bit more realistic because nobody was working on AI, right? But very few people were actually seriously working on it. There certainly weren't trillion-dollar AI companies, right? I think OpenAI is valued at like $500 billion now, but it's probably soon going to be $1 trillion, right? And you
Yeah.
know, so AI has become much more of an efficient market. So it's very unlikely that one small team is going to accidentally build superintelligence, right?
Well, let me try and, if I could just steel man the opposite case, I'd be
Mm-hmm.
very interested in your response to this. A steel man might be that we have seen those great leaps in capability before, like with ImageNet, right? Like the percentage completion there shot up by, I can't even remember how much exactly, but the Ilya submission was leagues above any other case from what I
But it was
remember.
still an incremental change, right? I mean, what you're talking about
Yes.
here is you're talking about some kind of neural network architecture that can recognize objects and pictures, right?
Yeah.
And, you know, before Elias Sutskever, you know, it was like recognizing 50%, and then after him it was recognizing like 75% or something. That's a huge leap. That
Still
25%
incremental.
increase is a huge increase. But, you know, in the grand scheme of things, if you're trying to build an army of Terminators to take over the world, having your Terminators image recognition skills go from 50% to 75%, that's not going to push you across the line from like I'm a couple of guys with a basement lab to I've literally built Skynet, right?
Yeah.
So even
Admittedly
even
so.
even
Yeah.
even technological changes that are um you know, quite radical for the research scene are not sufficient to take over the world from a small starting base. right?
But maybe the place where it could be is if that system somehow discovers some ability to self recursively improve.
Exactly. Recursive self-improvement. Now, if you go back to
Yeah.
sort of 2005-ish and you look at the kind of methods that Eliezer thought would lead to AI, he was thinking about Lisp programs, because I think he's done some Lisp programming, right?
Hmm.
I'm not a Lisp programmer. I'm stuck in I'm like a Python pleb, but a
God
lot of
bless.
people a lot of people are interested in these kind of like logic based programming languages. And he thought that maybe you could get a Lisp program that could rewrite itself, and then it could just rewrite itself to be more intelligent, right? And then once
Hmm.
it was more intelligent, that more intelligent version could write itself to be even more intelligent. Now, I think here what's happened is this is actually like a sort of deeply broken conception of what intelligence actually is, right?
Mm.
Um, intelligence doesn't work like that, right? You can't if you're slightly more intelligent and you start trying to do brain surgery on yourself to make yourself even more intelligent, and so on recursively, the result of that is going to be insanity, not genius. So actually being good at predicting what happens in the world relies upon observations from the world. You can't just like perform brain surgery on yourself to become a genius. Because and fundamentally the reason why is because if you did have the ability to perform brain surgery, just put aside all of the medical complications and the fluids and all that icky stuff. If you just imagine you could literally reprogram your own brain like you're a computer, right?
Mm.
You wouldn't know which changes are actually good, right? Because you already have, in order to be intelligent, you already have a brain that works pretty well in a lot of ways, right?
Yeah.
So to work out which changes will make it better rather than worse, you actually need some feedback from the real world, right? And so that's why what eventually worked was things like large language models, where they subject these models to an absolute torrent of data, right? You have like, trillions of data points that are put through these, and it's continuously trying to predict, complete the sentence or solve the challenge or whatever it is. And each task that it successfully completes contributes incrementally a tiny amount of extra intelligence. And the returns on this are typically logarithmic as well, which is a
Mm.
huge problem for recursion. Because if you have recursion with like logarithmic returns, that's not going to cause a singularity, right? Because if you get a little bit more intelligent and then the returns on that extra intelligence are only logarithmic, you're going to very quickly sort of plateau, right? So the way that we've actually gotten such impressive gains in the capabilities of these systems is by feeding them exponentially more data and exponentially more compute, right? And that's very bad news if you think you're going to do it recursively, right? Because you're going to need exponentially more compute and data. And then the recursive aspect doesn't even help, right? Like there's all of these companies, like there's DeepSeek and there's Meta and there's Anthropic and there's OpenAI, and they have huge amounts of money on the line. It's the most high stakes industrial and military competition in the history of mankind. And they're trying absolutely everything they can. And they have been doing so for about 5 years. And still none of them are actually doing recursive self improvement. And they've probably tried, right? Why? Because it doesn't work, right? I'm surely
Yeah.
they've tried this, right?
Oh, yeah.
Because again, if you have an AI and it has its own network and you just give it its own network weights, you say, okay, which weight should you change? Well, it doesn't know, right? Because the thing's a black box. The thing is it's a black box to us. It's also a black box to itself.
Hmm.
So it doesn't know what to change. It doesn't know which changes are actually good, right? So recursive
Yeah.
self-improvement doesn't actually work.
It doesn't
So,
have a
so, so
sufficiently accurate model of itself. Yeah.
it doesn't have any model of itself. It has no fucking idea how it works, right? Because
Yeah.
the weights of a neural network, they're just a bunch of numbers, right? These neural networks, their understanding of the world is very similar to ours. They don't have an innate sense of what the what the numbers in the neural network do, any more than you have an innate sense of what one of your neurons would do if you poked it, right? Your
Mm.
brain's like locked away in a skull where you can't twiddle with it, which is for your own safety to some extent, right?
It's
You
interesting.
know,
The parallels
right? Like
there. Yeah.
you don't know what that neuron is going to do. You don't know. So the way that you learn is probably also something like backpropagation, where you go through many examples of solving a problem. And as you do that, your brain updates the connection strengths or the connections. Now, just bear in mind, the way the real neurons work in the brain and artificial neurons in a neural network is not exactly the same. But there probably are some similarities. It's not completely understood, but one
Yeah.
story you could tell is that when you do a bunch of problems and you solve a bunch of challenges, each one that you solve incrementally contributes to changing the connection strengths between your different neurons and gradually changing your brain's algorithm to be closer and closer and closer to optimal, right? And so if somebody plays chess or tennis or something for a whole career, they've got millions of examples that they're using to make these slight incremental changes, right?
Subconsciously, even not consciously. Yeah.
Most of it's subconscious. Some of it is conscious. You can do learning consciously to some extent. But even when if you do something like language learning, right? When you're learning a language, you're starting to learn a new language and you have some logical rules that you know how to follow. And you sort of like, when you're trying to say something, you think, okay, well, I've got to do this, I've got to do this. It's this kind of verb. It's this, so I'll say that, right? And it's sort of very effortful and difficult, but you sort of
Yeah.
keep doing this over and over again. And as you do it more and more times, it becomes internalized. It becomes subconscious. Basically, there's a language model of your brain where you actually just update the effectively the weights or connections in that part of your brain until you basically build yourself a little mathematical model of the language you're learning, right? And then once you start speaking it, it just subconsciously activates and it just becomes completely natural and you don't have to think about it, right? And so as
Yeah.
a native English speaker, I've gotten to this stage with English where, I know technically that, there are a bunch of weird and wonderful rules about how you use tenses and, all sorts of other, but a lot of the rules of English, right? I don't even know, right? I know my brain knows the rule, it implements the rule, but I don't
Yeah.
explicitly know it, right? So recursive self-improvement for neural networks can't work, right? It can't, because the network doesn't have a model of itself, right?
Well, and let me
Because
see
that
if I
wasn't in
can.
its training data.
Yeah. It's interesting you say not in the training data. One of the things you were saying before makes me wonder, would you say that the thing we're missing is the ability to update the training data in a similar way that Yudkowsky is unable to update his training data?
You
Is
mean
that,
synthetic data? So you get the model to come up with scenarios of its own and then test itself on them.
well, even learning in context? I hear users complain all the time about how they have to constantly tell the model not to
Oh
use
yeah,
M
yeah.
dashes, but that is
Yeah.
baked
So
into its training.
there is one of the issues with current language models is they're generally they're not doing what's called online learning. So
Yeah.
in machine learning, there's this thing called online learning where you're solving a series of machine learning problems, and every example in real time, every example that you get right or wrong changes the model a bit. And for something like the YouTube recommendation algorithm, it actually does do online learning. So the model changes in real time as you thumbs up or thumbs down videos, or you watch them or skip them. YouTube will train a model specifically for you. Every user will get its own model.
It's pretty
Probably
neat.
not a neural network model, but it can be. You can use neural networks for recommendation algorithms. Typically, you
Hmm.
don't. But it will train a model for each user, and that will be updated in real time rather than some kind of batch update. So the current language models, most of them, I believe, do not have like online learning. Like, they don't change their weights in real time, right?
Which seems to be
But
somewhat of a control measure because the companies wouldn't want users to be able to push the models outside of a certain distribution.
well, one problem is if you have the model updating its weights, you're going to
Yeah.
have one copy of the model per user, right?
Hmm.
Because you can't
Hmm.
have you talking to the model about your, I don't know, donkey porn addiction, and then I start talking to then I start talking to about it, starts coming up with donkey porn, right? Like, I don't
Yeah.
want
Yeah.
this, right? You know, uh, so you'd have to have one per user, right?
Yeah. Yeah. Makes sense.
And suddenly, that's extremely expensive, right? Now you
Yeah.
can probably do like low rank adaptation per user or something like that. But I think basically at the current point of commercialization of this, it's not worth it to do that,
Hmm.
right? It will probably happen over the next 5 years that you will get per user online learning customized models, but it's an additional cost that people may not be willing
Yeah.
to pay. And the hardware for the the sort of GPUs are not really GPUs; they're specialized AI sort of supercomputer type things that are evolved from GPUs. Those are extremely expensive. They're extremely scarce. GPU time is a scarce resource, and so the AI companies are not going to provide personalized models until the hardware gets cheaper to the point that they can do it.
Yeah.
Because doing training on these models is expensive. It's very expensive, right? To train one of these models, you're talking about $100 million in just the hardware and electricity costs, right?
And climbing, right? I mean, it's still an escalating cost from what I understand. They're
What
pouring more and more resources into it,
did
into
you did you
training.
say? Did you say climate?
Climbing. The cost of the training is still
Oh,
climbing. We
increasing.
haven't
Yeah,
seen
it
the
is
ceiling.
increasing. Yeah,
Yeah.
it is increasing. The
Yeah.
reason it's increasing is because they keep making bigger models. Because you see, the economics of this is there's a lot of people who use AI, right? So I think there's something like about 1 billion users for these AI models, right?
Unbelievable.
So if a
Yeah.
model costs $100 million to train, but it's split between 1 billion people, right? Suddenly that's not actually that much. That's like what, 10 cents, right? If my math is correct there. Would you pay
Hmm.
10 cents to have access to an AI model? Hell yes,
Oh,
right?
every day. Yeah.
And of course, there's also the inference cost because inference is not free, right? The training requires training requires like 1 trillion backwards operations. Inference probably requires a couple of thousand forwards operations, and a forwards op and a backwards op are kind of roughly the same cost. So training is
Hmm.
like 1 million times more expensive than inference for a base LLM. Now, if you have one of these reasoning models, it has to do multiple sentences. It has to do a lot more forward passes to get to the final answer. So it's consequently more expensive. But you can do reasoning
Hmm.
with like a smaller model to try and sort of compensate for the increased number of forward inferences. But basically, if you think about it like this, right, the basic LM, if it costs $100 million to train, but you share it between 1 billion people, it's very cheap. But now, if each one of those billion people has to have their own personal customized model, even if the customization only costs $1 million instead of 100 million, so it's only 1% of the total effort. Now, instead of paying 10 cents for
Yeah.
AI, you have to pay $1 million for it. Oh, that's a little bit different. Okay.
Yeah. The
Now
scale
you're
gets
like,
out of hand.
I'll do without the customized model. It'll talk about my favorite topics.
You can go with the
What,
general porn category instead of that
whatever they
specific
happen to
niche.
be. Whatever they happen to be. Yeah, yeah.
Yeah, yeah. I mean, the internet is for porn. It's kind of surprising me that AI hasn't
Well,
dug
I mean,
more in
it
that
has. It
direction
has.
more rapidly. Yeah,
Elon has
yeah.
unleashed it with the Grok models. I haven't personally used them in that way. It doesn't particularly interest me, but I know some people have. But yes, I mean, basically, the economics doesn't support it, but there's no technical reason that I'm aware of that you can't do online learning with LLMs.
Yeah. Stepping back to the self-recursive improvement cycle, what I was hearing you
Mm.
saying, because I know that like OpenAI is now using Codex, they say, for a majority of their code generation. In some sense, that's recursive self-improvement.
Okay, but
But what you're
this is
saying is
recursive. Yeah.
divorce
Okay. So this is recursive self
the
improvement of the industry as a
not
whole.
self, not
Yeah,
outside of human
it's not an
dumping
internal
more and more
system.
information
Yeah,
into it.
right. So you can
Yeah.
have a situation where you have a whole firm or a whole economy, and it starts to use AIs in its own processes. So that starts to do. I'd call this dog fooding rather than recursive self improvement. After the
Interesting.
Web
Yeah.
2 developers, when they use, like, if people at Microsoft use Hotmail or Office, they call that dog
Their own
fooding.
product.
I think there was an American
Yeah.
company that said something like, "Our dog food is so good that we eat it ourselves," and it's stuck as a term, right? They call it. Says now, if you use your own
Yeah.
products, you're doing dog fooding. So this isn't really recursive self improvement so much as like AI dog fooding. And I don't think the implications of this for alignment are anywhere near the same. Because if you're just doing dog fooding, if
Mm.
Claude is being used in the Anthropic office, well, that's not the same as leaving Claude in a server, in the basement over the weekend to just like tweak its own weights, and by Monday morning it's turned into the paperclip maximizer because its recursive improvement got out of control, right? Dog fooding, it's like you're like, okay, Claude, write this code. Okay, Claude, filter these training examples and so on and so forth, right? I mean, yeah, maybe there are some risks that you could have, but it's like just a completely different scale of and severity of risk compared to the traditional Yudkowskian scenario of the AI is stuck in the server on its own, twiddling with its own brain that comes out as some kind of Cthulhuid monstrosity that goes and destroys the world. There are two big things that the Yudkowskian concept of AI risk was wrong about. Number one was alien values. He was wrong about that. Number two was recursive self-improvement. He was wrong about that, right? And if you take those two things out, then the case for Yudkowskian type AI risk based upon paperclip maximizers and the AI not understanding human values and not internalizing human values and being misaligned, all of that stuff really kind of goes away. And what you really end up with is a scenario that's actually a lot closer to what Robin Hanson came up with in his book Age of M, which is again a masterpiece, right? Where basically, instead of thinking of these things as these alien monstrosities that are going to turn the world into paperclips, you just think of them as sort of digital humans, right? Now, it's not quite like that, but it's a lot closer to that. And these sort of digital humans there's no real issue with alignment problems because the firm that creates these digital humans has quite a lot of control over the process it creates and maybe doesn't have full insight into how they're created because of black box functions. But I mean, like you can try out 100 different variants and you can do reinforcement learning on them and you can do all sorts of things to make sure that the ones that you deploy in practice are relatively well aligned. And if you as a company deploy an AI system that's not very well aligned, well, you're probably going to lose business because there's going to be competition, right? So this is another thing that the sort of Yudkowskian picture of AI risk doesn't quite get, is that if there's a world in which nobody believes in AI, and there's one team working in a basement to make an artificial intelligence, and they leave it over the weekend and it turns into a super intelligence and the paperclip maximizer goes and kills the world, that's one thing. But a different scenario is one in which there are many different companies and they're all competing and the technical frontier is a relatively efficient market. So there isn't any strong technical lead that any one company has over the others, right? I mean, and we saw this with DeepSeek because people thought, oh, OpenAI has pulled off reasoning models. So that's an unassailable technological moat. Nobody's ever going to catch up with OpenAI. OpenAI is going to take over the world. And then a couple of, 6 months later, DeepSeek basically just did the same thing and they even did it a little bit better, right? So it's just going to be like that. It's just going to be, there's going to be an efficient market. You're not going to be able to take over the world with AI, whether it's aligned or misaligned, because you're never going to have that kind of lead over the other companies, right? And that comes from this thing of logarithmic returns to scale being a form of diminishing returns. So, when you make your AI 2, 4, 8, 16, 32 times bigger, and you spend 2, 4, 8, 16, 32 times more compute on it, each of those steps is a doubling in the resources and cost of your AI, but they each get a constant improvement in performance. So because of this, it's very hard for one company to pull ahead because, you might have 2 or 3 times more money to spend than your competitors, but they're only a fixed amount behind you because when you're at level 16, they're going to be at level 8. And the difference between level 8 and level 16 is the same as the difference between level 1 and level 2, right? So it's not actually a very big difference. So logarithmic returns to compute, model size, data set size, this is all typical for any kind of machine learning work, give you diminishing returns, which give you a relatively competitive, efficient market in building these things. So as long as one particular company doesn't have an absolutely disgusting resource lead, you have this efficient market where nobody has enough power to actually, corner the market, take over the world, and things like, building nanotechnology, right? So Eliezer's scenario was that this AI would recursively self-improve by twiddling its own brain, which now we sort of know probably can't happen. But as a result of that, it would develop nanotechnology, right? But, again, I mean, people are trying to develop much more basic scientific applications of LLMs than developing nanotechnology, and it's not working yet. right? Because it's
Mm.
hard, right? It's hard. It doesn't come automatically. It's difficult, right? And because it's difficult, what will happen is people will make incremental advances, right? So maybe in a couple of years, we'll see an AI that can, make simple engineering discoveries that actually work, right? But we haven't really seen that yet, right? So what's happening at the moment in things like mathematics research is expert mathematicians are using AIs for some of the grunt work, right? So they're not actually smart enough to prove an interesting new theorem. But if you've already sort of found the general form of a theorem and you need to go on some kind of hunt for the right specific parameters, then the AI can probably do that for you. So what we seem to be seeing is this incremental um, improvement in performance, which is both incremental and relatively widely distributed amongst these companies. And that situation is
Yeah.
not very friendly to the idea of a single AI being strong enough to take over the world. So not only is alignment not a problem, right? Not only does recursive self-improvement not happen, but because returns are sort of diminishing and in fact logarithmic, nobody ever gets far enough ahead to actually take over the whole world, right? So it just isn't playing out the way he thought it would, which is often the case. If you just sort of theory craft a lot, you're eventually going to make some mistakes, and those mistakes are going to compound, and your picture of the future is going to be completely wrong, which I think is what's happened to basically the less wrong consensus on AI risk. But the thing is, you have to understand, I was there in 2007, 8, 9, 10. Even to say that we would get AI was like, that was saying something, right? That was really sticking your neck out,
Yeah.
right? So, it was an impressive worldview for the time. It just hasn't aged very well
Oh yeah.
because reality turned out to be different in multiple different ways from what people like Eliezer and maybe even to some extent people like Nick Bostrom, although I think Nick Bostrom was more cautious with his prognostications on this. But I think Nick Bostrom was also worried, and Stuart Russell was also worried, again, for similar reasons. Stuart Russell has a slightly different way of putting it. He talks about maximization of functions being dangerous because when you tend to maximize a function, it produces undesirable results that are not the same as if you just sort of try to like increase it a little bit, right? He said, look, if we build some kind of AI system that sort of seems like it's aligned with human values, and then we start to maximize against it, it's going to produce a moral catastrophe. But the reason that turned out to not be correct is because the way that the AI industry works isn't by having one single system that we just send off into the world to like, okay, go and do your thing, maximize everything. It's incremental. It's like, well, this company releases this system and this company releases this system, and none of these systems actually generalize in terms of capabilities very much, right? So, you have a particular system that's hot for 1 or 2 years, maybe even just 6 months. It's kind of good, but then in 6 more months, a different system will supersede it. So you never have one system that has the ability to control the whole world and whose capabilities
Mm.
generalize far further than its creators really imagined, right? Probably the closest that we ever got to
Yeah.
that was when OpenAI was the only AI company, right? When they released GPT-2 and GPT-3, that generalized potentially quite a lot further than they were expecting. And the reason that it happened was because the market wasn't very efficient at that point in time. There was only one company doing it, right? So when they pushed, they didn't know how far their push would go because nobody else was pushing, right? Like how open, if you push against an open door and there's like a blockage against it somewhere, you don't know where the blockage is. Once you hit the blockage and there's some pushback, right, then each push tends to produce a sort of smaller increment in how open the door is. And I think this is kind of what happened with
Mm.
LLMs. The most shock and the most surprise happened early, not late. Because early on, when the models are small relative to the total amount of compute in the world, right, you don't know how much bigger you can push them until you really start hitting strongly diminishing returns, right? So you make a small push and it works a
Yeah.
bit, and you're like, okay, let's make a bigger push. And then it's like, whoa, this thing can do in-context learning and it can translate languages and it can, whoa, we weren't expecting that. But once you have many, many companies and a significant fraction of the world's compute is dedicated to AI, every direction that you can push in has already been pushed pretty far, and all of them have hit up against whatever their hard technical limitation is. And so now incremental progress is difficult. So you're probably not going to be surprised that much. The Yudkowskian paradigm says that the amount of surprise will accelerate over time, because at first you'll have a model that's not very good, and then you'll have a bit better. And then once you get a good one, it'll start recursively self-improving itself, and its intelligence will start like increasing exponentially or something. But that's actually not what happens, right? What happens is when the models are small, they improve quickly because like you're small, and so the low-hanging fruit are yet to be picked. But once they're quite big and they're pushing up against the state of the art, they're pushing up against these diminishing returns curves where you're already spending like $1 billion in compute to make it. And the jump from 1 billion to 2 billion is the same as the jump from 1 million to 2 million because of logarithmic returns to scale, right? So, before you only had to spend $1 million to get that increment. Now you have to spend $1 billion. So the amount of incremental progress you get per dollar has reduced by a factor of 1,000. So rather than an exponentially increasing singularity, you actually get a logarithmically reducing situation where things get harder and harder and harder to develop. But the amount of capital going into the space continues to increase. So we actually still do see progress until we hit like a capex ceiling, and then the AI bubble probably bursts, and we get a sort of 2000 scenario where there's like a mini AI winter where a lot of people have to lose a lot of money, and the industry has to sort of rationalize a little bit and consolidate into the applications that actually work. And then potentially a sort of a second growth phase where we do see sort of sustained growth, but that sustained growth will in this sort of more sustainable phase be based upon using robots and AIs to construct physical infrastructure, right? Go out and colonize the solar system, colonize the oceans, whatever. But that's probably not going to happen as long as we can still get improvements by just making the models bigger.
I want to talk about your seasteading concept, your ice steading concept rather, because that is fascinating. Before we jump to that though, this whole idea of government by AI, one of the themes of my podcast that I try and ask everybody is, would they vote for an admittedly fuzzy concept of an ASI in 2028? You've, I think, pegged the concept of AI governance to two specific criteria: that it has to be open source and that it has to be in some way public ledger based or blockchain based. Is that an accurate summation of your view, or
not really?
What do you think about that general concept? What would it take for you to commit your vote?
Yeah, I wouldn't say I've gone strongly in favor of open source, but I think generally open source is good, but I'm not like a zealot. I do think that some kind of digital ledger, so crypto-based system, is what's needed to give people faith in AI governance. I think the problem at the moment with AI governance is the AIs that we have at the moment are good at talking, right? But they can't. How can I describe it?
Yeah.
They're not trained to be good at governing, right? So you can ask a language model, should we invade Iraq? Whether you should do a military invasion, what you should do with interest rates, etc. You can ask it, but it's not really trained to be good at those kinds of things. I mean, to be fair, neither are human politicians, right? But human politicians have a lot of machinery that helps them out, right? So they have human experts, they have institutions, they have sort of, things like universities and research centers, and they have a whole lot of machinery that allows human politicians to have like a baseline level of competence that I think is, and not just competence, also coherence of their strategies, right? Might sound a little bit strange for me to tell you that human politicians have coherent strategies, but compared to what an LLM would do, right? So modern LLMs are really, you should think of them as, if it was a person, what kind of person would an LLM be? It would be like a sort of very encyclopedically well-educated sort of genius, maybe not quite genius level, but high middle level IQ person who had
idiot
like
savants.
very severe, not quite an idiot savant, but you know, because they're kind of like normal people. They can answer questions about, you know, social life and so they're not like super nerds, right? So they're quite well
Mm.
rounded in terms of their personality. But what they have is they have this sort of strange memory loss slash ADHD problem where they can't really entertain a coherent thought for more than a couple of sentences. Like once you get into like a very long conversation over hours or days, they will lose any form of coherence, right?
Mm.
Now this is sort of slightly improving as we make the context windows bigger and, you know, retrieval, and there's a whole bunch of technology. But basically, right now, if you asked an LLM how to govern the country, the answers that it gave you would basically be kind of seat of the pants answers that wouldn't really be particularly good.
Mm.
So we need to improve the technology. We need to actually train AI systems that are actually good at governance, right? And in particular, as a subset of that, we need to, or as a subcategory of that, we need to train AI systems that are good at making accurate predictions, well
Yes.
calibrated, accurate predictions about the real world. Because right now, if you ask AIs for accurate, well calibrated predictions about the real world, again, they're kind of seat of the pants. They're not really much better than just asking someone off the street if that person happens to be relatively well educated. And that's not good enough, right? So we need to make AI systems that are highly trained at prediction. We need to basically make artificial super forecasters. Because you've heard of the super forecasting movement, right?
Yeah.
People who spend all of their time assigning probabilities and forecasting events. So we actually need to train AI systems to be good at that. And they will probably be superhuman at super forecasting, right? So maybe you call them super forecasters. I don't know. That sounds a bit lame. Ultra forecasters. Um,
Mega
so
forecasters. Yeah.
mega forecasters, yeah. We're going to train these ultra forecasters that are very good at predicting future events. But that's not quite enough on its own. We also need them to be able to predict counterfactuals. So a
Mm.
counterfactual is something that doesn't happen or might
Yes.
happen but could. And so
Yeah.
counterfactually, if I put my hand on the oven, would I get burned? Yes, I would, even though, in fact, I've never done it, right? I don't
Well,
have to do it. Yeah.
if I can just say, it's fascinating you bring up the counterfactual there, because I think that is where humans run into the most problems, is we operate under a kind of tyranny of the counterfactual. For
Mhm.
simple physical systems, yes, we can accurately say if you put your hand on the stove, you would have gotten burned.
Yeah.
But when it comes to trying extrapolating out these global or even national, state, or local policy changes, I think we often fail to see how those ramifications would play out in reality. So we make these grandiose
Yeah.
claims, you know. But
I think human politics, especially human democratic politics, has several problems. It has some incentive problems,
mhm.
but it also has some intelligence-based problems
Mm.
where the average person is actually disappointingly cognitively limited, should we say? um, right? You know, the average person has a good grip on how to interact socially, most of them, right?
In their
And they
local
have a
frame of reference,
and
yeah.
they're the frame of reference, and they have a good grip on whatever practical things they have to do in their day-to-day lives. So if somebody's
Yeah.
a car mechanic, you know, they probably know not to stick the spark plug up the exhaust pipe, right?
Mhm.
You know, I mean, they're not going to do obviously stupid things like that. But if you
Yeah.
ask them something like, well, you know, couldn't we solve the poverty crisis by just printing more money? And they're like, yeah, that's great. We can print more money and give it to everybody, and then everyone will be rich. Right?
Yeah, yeah.
So most people don't have the mental models necessary to really understand like governance for human society, especially like a big human society with like America is nearly 500 million people. That's
It's crazy.
a crazy amount of people, right?
Yeah.
Um, People are used to governance of maybe 100 people because that's like the Dunbar number. That's the size of a tribe. So if there's anything you can do with 100 people in terms of their governance and politics and interaction, people will probably be pretty good at having a seat of the pants guess of like, yeah, you know, that guy seems to be cheating everybody. We should ostracize him, right?
Yeah.
People are pretty good at that. But when it's questions that affect how 500 million people are going to interact, and especially once you have all of these systems, like money is a system, right? And the economy is a system, and the healthcare system and the science system and the information system like news and debate and stuff like that. We have all of these systems. People's sort of seat of the pants idea about how to run them is really bad. People have no idea, right? They have absolutely no clue. And so because of this, it's very easy for politicians and insiders to kind of scam people, basically.
Yes.
And so if you look at what's going on with politics, a lot of it is basically rent extraction by scamming people. But the scams just get more and more complicated. I mean, in some cases they're not that complicated, but I mean, one thing that's sort of going wrong in Britain at the moment is basically taxes are too high. And there's this thing in economics called the Laffer curve, where if you imagine increasing the tax rate from 0% to 10%, the government gets more money, and then from 10 to 20%, the government gets more money, and so on. But when you increase the tax rate from 90% to 100%, that doesn't generate more money. 100% tax, you're going to generate less revenue.
Yeah.
Generate
It's
a
kind of
lot
the
less.
parasite problem. It's how much
Basically.
can the parasite extract before killing its host.
So what's happened is the government's turned into this parasite, and it's hard to explain to people just how bad this has gotten, because number one, the concept of something like a Laffer curve is difficult for people to understand, right? Number two, there's a lot of facts that are a bit obscure and kind of boring, and most people don't care about them, right? Like, what is the marginal tax rate for this? What is the benefits you can claim? Blah 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 blah. So there are a lot of things that people just don't understand, don't care about, and don't have a particularly good intuitive understanding of, where I think especially trained AI model would be much better. And if you base that AI model on a sort of digital ledger technology, so that the computation itself was represented on a blockchain, people could be fairly confident, especially intelligent people could be fairly confident that they weren't being scammed or lied to, because this thing would be doing its computations either in public or semi-public. So, for example, instead of having your governance system computing in public, you could have it record encrypted versions of its computation, which would then be redacted or unredacted like 5 years later, right?
Yeah.
So this or 3 years later, or even 6 months later, right? Depending on what the task was, because this would mean that people couldn't attack it in real time by knowing what it was thinking, but everything it was thinking would be recorded for future assessment, so that people would have confidence that there wasn't a scam going on that they were never going to find out about. And you could also
before
have
it crashed the market, like a Madoff or something.
Yeah, you could also have automated monitoring of the governance system by algorithms which were open source, or models which were open source contributions, which themselves would log their outputs, which would be unredacted 6 months later. But maybe in real time, they would be able to give a compressed, redacted warning of like, warning, I think the model is doing such and such bad thing. And if enough of these warnings were triggered, then maybe you would have to actually unredact in real time, right? So there are various ways
That's
you
fascinating.
and people could submit these algorithms themselves. So you could have open source enthusiasts. So instead of having a bunch of, because Elon employed all these kids, all these little teenage boys to do the Doge thing, instead of having like a bunch of smart teenage boys to audit the government, you just have a bunch of open source models that are constantly auditing your governance model and what it's doing, right? But because they're models, they can be run, encrypted. They can be, run using holomorphic encryption or something like that, so that nobody can possibly know all of this stuff in real time. And so there's only selective disclosure of what's going on. Because one of the problems with running a fully open governance system is you're going to actually disclose too much material. You're going to disclose too many details, and that's going to make it easy for outside threat actors to take advantage of it, right?
Yeah.
So you're gonna have a too much openness problem rather than a not enough openness problem. But I think it's solvable. So I think if you train a governance model to be good at governance, right, and you use digital ledger technology, use blockchain technology to make it transparent, at least retrospectively, I think you can come up with a significantly um what we might call more trustless, because you don't, it's like don't trust, verify.
Amen.
um so a more trustless form of governance, but also a more competent form of governance. And I think you need both. I think people will not put up with trustless governance if it's incompetent, right? But
Yes.
they will put up with competent governance that they have to trust. And that's kind of the problem. Now, human governance tends to be neither, right? It's neither competent nor trustless, but it's
Yeah.
all we've got. And then you have things like Elon, which is sort of competent but not trustless. You have to trust Elon, right? You have to make a personality call, a judgment call based on his personality that he's going to do the right thing,
Hmm.
which I think is mostly correct in his case, but it's always fragile. It's always a single point of failure if you have to trust a person or a system to not lie to you. But I think automated governance can be
Yeah.
made quite trustless, and it can be made super competent eventually.
Yeah, and I've heard you speak about Curtis Yarvin's patchwork philosophy and
Mhm.
comparing that to your Elysium protocol or concept. I
Yeah.
don't know how you model that exactly, but do you view something like Curtis Yarvin's patchwork concept ultimately resulting in that kind of AI governance? I haven't heard him reference
Well,
like the
I've talked.
ultimate
I actually
CEO
met.
as an AI, but
Yeah, I actually met Curtis, and I put this idea to him in person, and he
yeah,
doesn't like it. But I think he's just a bit too much of a boomer. Well, he's not actually a boomer. He's a Zen. He's a Gen X, isn't he? But I think it's a little bit
yeah,
too techie for him. He doesn't like it.
that's
He
crazy to me. I mean,
he
it
fu-
seems to
he
fit
fu-
so perfectly.
it does. I mean, he seems to fundamentally think that computers are never going to be given the power and responsibility to actually implement their recommendations. And because
Mm,
of that, he doesn't think that it's particularly interesting. He thinks that you always need a flesh and blood human, sort of corporate king slash,
dictator.
CEO.
Yeah.
Effectively something like a dictator, except it's supposed to, have some like property rights and exit rights and stuff like that. The problem is if you have a dictator and you want to have like exit rights and you want to have fair competition, stuff like that, I don't think that giving your citizens exit rights and giving other dictators fair competition over the land, I don't think that's actually the Nash equilibrium. I think we have plenty of experience with dictators and kings and stuff on Earth, and their incentives are very much not to do that, right? Their incentives are to trap people in their countries, force them
Yes.
into being soldiers, and send them to the front lines in order to unfairly take over other people's countries, right? Which is kind of what Vladimir Putin is doing right now. I'm not really particularly strongly anti-Putin, but if you just want to see Putin as the most faithful representation of the Yarvinist idea,
Yeah.
Putin is kind of quite close to being the dictator of Russia. He's not quite there, but he's quite close to it. And so what's he doing? He's trapping Russians in Russia, and he's kind of forcing them to go to the front. Well, not exactly forcing them. He's using contract soldiers at the moment, but he kind of wants to force them to go to the front line. He doesn't. If he really was dictator, he probably would. He did actually try it. He did try mobilization, but it was very unpopular. So basically, what the dictator wants to do is he doesn't want to run like effectively a countryside hotel for people that they can enter and leave as they wish and freely, go to other jurisdictions. He wants to run a dictatorship, dictatorship nation that's going to maximize his personal power,
Yeah.
and he's going to want to conquer other countries, not trade with them. And he certainly doesn't want his talent to go and escape to other countries where he doesn't get to tax it, right?
Yeah.
So,
Every
I think
dictator is a singleton at the end of the day.
well, not just a singleton, but kind of like a singleton with some fairly bad incentives, right?
Yes.
It's sort of misaligned in a lot of ways. Dictators
Yeah.
tend to be misaligned from their people.
Yeah.
Not in all cases. So you have people like Lee Kuan Yew who were kind of very patriotic and wanted what was best for his people. And so Lee Kuan Yew kind of was a dictator, but he kind of was a benevolent dictator.
Mm.
And I think if you had Elon Musk in charge of a country, like if he's in charge of the Mars colony as like the king of Mars, I think he would probably be a pretty good king. But the problem with kings is look at Elon Musk's children. One of them turned out to be like a radical leftist transgender. And so this is how monarchies actually fall apart. You have the king, the father who built the empire, and then his son turns out to be, a little bit different, right?
Yeah.
So I think Yarvin has pushed a long way on the right path, right? But he doesn't want to go all the way because he fundamentally doesn't trust computers to be able to wield power. It's sort of like the concept doesn't quite fit in his in his Gen X brain.
Yeah.
But I think that is basically where it's going to go, right? I think it's inevitable that people are going to want governance by AI because it can be both more trustless and more competent. And I think the innovation in increased trustlessness will perhaps be as important or more important than the increase in competence.
Yes.
But I think you need both.
Yeah. It reminds me of what you were saying of the recursive self-improvement point, is that dictators can almost become recursively self-devolving. They
Yeah.
can get stuck in local minimas. Whereas if you
Yes.
have that AI system that is reliant on its populace for the generation of data, for the direct input.
I don't think it's going to be reliant on the populace of the generation of data for much longer. I think we have a
Mhm.
relatively brief period where humans are still going to be generating useful data, but
Yeah.
it's not going to last much longer.
Well,
Um,
and this is a point that I've heard Ilya say too, is that the internet has basically been mined out. We've already
yeah,
sucked out all the oil from the internet, so to speak.
yeah,
But there's
exactly.
so much, there's a magnitude of data more available in the real world. There is so much data that is not captured on the internet yet, even.
The problem
Not even
is,
the most efficient
yeah,
internet.
the problem is internet data. The average internet data tends to be quite useful. So if you read a web
Yeah.
page about something, that web page, somebody went to a lot of trouble to create it. And so the information they put on it is probably relatively honest, relatively accurate, and relatively important. Whereas, if you're collecting data from the real world, if you just look at a security camera, so let's say you get every security camera feed in the world, right? Well,
Hmm.
any one particular security camera feed is going to be almost entirely useless. Maybe very occasionally something interesting will happen, but for most of
Yeah.
the time, that feed is just going to be a picture of a relatively static scene with a few leaves blowing around in the wind. And that data is not worth the same amount of utility per byte as, say, a YouTube video or, for example, even this conversation, right? Because this
Curated.
conversation represents a compression of quite a lot of real world experience and knowledge and information from other people and computation and all sorts of things, right? So not all data is equal per byte. And the problem is the stuff that we've mined out is actually the good stuff. It's the rich veins of useful information. And the stuff that's
Mhm.
left over is basically the garbage, right? With very little value per bit. Now, of course,
Yeah.
they're going to suck up that garbage and see what they can get out of it, because why not, right? But you're not going to get the same level of gains from it in terms of capabilities. So in order to get good data that isn't internet data, you're probably going to have a lot of either synthetic data from dedicated environments, which is what Mechanize are working on, or you have like artificial laboratories. And I think there's a startup, I can't remember the name of it, that's recently launched that's going to build an artificial laboratory for AIs to do research on.
Yeah.
Because the data that comes from a research laboratory where you have a microscope that's looking at a petri dish or something like that is much more valuable per byte than the data of like a camera looking out at the street and seeing some leaves blowing around, right? You're not really going to learn very much from that. I mean, yeah, it's like somewhat useful for maybe for pre-training a vision model or something like that. But once you've got a good vision model, the incremental advantage you're going to get from, say, a security camera footage or a car dash cam or something like that is not going to be very big. It's not going to be
Mhm.
nothing, but it's not going to be very big.
Yeah. I wonder if you see an overlap, though, mentioning taking out all that highly curated data, the
Mm-hmm.
cream of the crop, so to speak, and the kind of plateau that we've seen in academic literature, where we're now running into all these replication crises. Because in some ways, the academic literature has become divorced from reality. They started
Yeah,
playing a game.
I think academic literature has more of an incentives problem than a data problem, though.
Yeah.
Science has become quite corrupt.
Yeah.
And I
Is
sort of
there not a
experienced.
similar incentive problem with the internet data, though? Like people are projecting an image of themselves in a way that is not always faithful to
Yeah,
reality.
yeah,
So
yeah,
if
yeah.
you had
There's
both
yeah.
the internet data and the real time data, the real life data, you could not only get an order of magnitude increase from the real time data, but
Mm.
also the comparison between the two.
Yeah, to some extent, but I still think per byte
Mm,
data from security cameras and dash cams and you know whatever other data source you can find, it's just
yeah.
not going to be as good per byte. So
Mm,
maybe you have to process 10,000 times, maybe you have to process 10,000 megabytes of that kind of data to get as much value as you got from 1 megabyte of YouTube videos.
yeah.
Because YouTube videos tend to be about useful, interesting, notable, or important things. Whereas the average security camera or dash cam or some other sensor, maybe like a Wi-Fi network sensor data, is unlikely to be particularly on its own useful, interesting, or important. And
Fair.
maybe if you sift through 10,000 hours of car dash cams, you see something that's kind of actually going to update your model a little bit at the
Mm.
margin compared to 1 hour of YouTube videos.
So you
So,
think synthetic data is a much more likely way for.
um, well, it depends how you make the synthetic data, though, right? So, you can use the output of an LLM to train another LLM,
Mm,
right? But there's a sort of law of conservation of information here where you kind of can't, there's no free lunch. If you have a model that doesn't know how to do something and you get it to produce a bunch of content and then you train another model on that content, that new model probably still won't know how to do the thing, right?
yeah.
Maybe there are some cases at the margin where it can work, but I think that's the big picture idea, is there basically isn't a free lunch with synthetic data.
Hmm.
I mean, there is to some extent where it sort of makes up for the inefficiencies of, gradient based training. So you do get some improvement, but it's like it saturates, right? I think people have
Hmm.
done empirical experiments on this and found that after about you can get a lot of benefit rather than making synthetic data. You just show the same data to the model 5 times over in a different order,
Really?
right? Yes, and you get improvement, right?
Wow.
But after about 5x, the improvement starts to saturate and it goes away. And this is just
Huh.
sort of making up for some of the shortcomings of the training algorithm, where if you only show the model once, it might not really learn it. It's kind of like that with people. You have to give people several examples of something before they really get it. And
Yeah.
neural networks turns out as similar to that. So
Hmm.
just showing the model the same data 5 times is worth something. And showing it some synthetic data that it either generated itself or that a similar model generated is also worth something. But the gains
Hmm.
do top out. You can't just keep doing that forever. If you try this infinite loop of synthetic data, you'll actually probably get model collapse, where the models will come up with effectively hallucinations that will start to dominate the process. Effectively, like imagine like a cult that all they do is read their own writings and they never go out. Oh wait, I'm
Yeah.
not talking about. You see what I mean, right? You see what I mean. So
Yeah.
basically, there's a limited extent to which that works. So I think a lot of the progress that we will see, instead of generating synthetic data from neural network based models, we will generate this synthetic data from deterministic simulations or proof engines or stuff like that. So
Mm,
one of the best combinations that you can have is where you have an LLM which is trying to solve a mathematics problem, and then you have a
mm,
proof checker which is checking its proofs, and that's a deterministic process,
yeah.
right? So one of the nice things about mathematics is if I give you a automated or a sort of a digitally annotated proof of a conjecture, you can deterministically in fixed time check whether that is a valid proof or not. So if you have a neural network that's a generator and some deterministic system like a proof checker that's a checker, well, there's sort of unlimited value that you can get from that, at least within
Yeah.
the rules that system can check. So I think it's plausible this is how we're going to get superhuman mathematicians. by combining neural networks with proof checkers. And I think personally, and this is probably going to, I don't know, this might surprise you. I think the way that we're going to get superhuman governors is by having models of society that we build and having AIs actually effectively play, sort of like play civilization effectively, but with a relatively good model of how society works. Nobody's actually bothered to make models that are this complete and detailed yet, but I think that's how you would do it.
And
Or
that
at
makes
least,
total sense from the perspective of your Elysium proposal, because
yeah.
potentially humans could inhabit some of those virtual simulations as well and be like on the ground proofs that the world is not only coherent, but preferable to their preferences.
Well, one of the advantages of having a simulation that's fully digital is that you can run it very quickly, right? So you wouldn't want any humans in it. You wouldn't want any human input. Probably. So there is kind of like an interesting historical example of this that's a bit nerdy. You heard of like Warhammer and Warhammer 40K and stuff like that?
Oh yeah.
People play like with the toy soldiers and stuff. Do you know what the history of that stuff is? Like, where did that come from?
It was a spinoff from D&D or something, right?
Kind of, but it actually goes back to what's called Kriegspiel, which is the Prussian army actually used to have. They invented basically a version of like Warhammer where they would play on a tabletop with dice with units of men, and this was what they did at their officer training school to train their officers how to fight real battles, because a lot of the dynamics of a real battle don't need actual real soldiers, right? It's just enough to have, here's a group of men with this weapon, here's a group of men with this weapon, here's the terrain, we're going to charge, we're going to shoot, or whatever.
Yeah.
You can just simulate that with a dice and with a board, and it's good enough that the Prussian military was using it to actually train people. And in World War II, something similar happened. So there was a big battle in the Atlantic between the Axis forces, particularly the Germans with their submarines, and the Allied forces, particularly the British and Americans, doing anti-submarine warfare and convoys. And they actually also implemented effectively a naval tabletop simulator campaign in order to try various tactics and strategies and stuff like that. And they even had a very interesting technology, which I heard about on like a video or a podcast or something. I think it was to test something about something to do with like code breaking and like how much value you actually could get from breaking the enemy codes, because they had some ability to break codes, but it was limited, and they wanted to test like how much more resources they should put into that. So what they did was they had a game board that had German like model submarines on it and model convoys, and they had a bunch of naval officers playing the Allies, and they had a bunch of, I think it was female Navy officers playing as the Germans, and they put like they put like a translucent brown screen in between the two sides, and the way the colors worked was it meant that from one side of the screen you couldn't see where the submarines were, but from the other side of the screen you could. And this was a way to test, or maybe it wasn't every submarine, but it was like certain of them. They were colored in a certain color so that from the wrong side of the screen you just couldn't see where they were. And so they used like some quite sophisticated simulation like techniques, like putting like translucent screens and having, modeling all of the positions and modeling the ability to intercept communications. And because this was basically a model with randomness, with partial observability, with rich state, even with like people giving each other orders, and you wouldn't, all the naval officers couldn't just confer about what to do. One would have to say, okay, Captain so-and-so, this is your order, go and hunt that submarine, I think it's in this square, and so on. Right, so they had quite a sophisticated naval tabletop campaign game that they were using to test out what's going on in the real world. So I actually think that there probably is viability in having basically stateful, complex representations of the world and using those to train models to be good at governance, strategy, etc. Right? And I think people are going to start doing that relatively soon. I think there have been some papers that are at least pushing vaguely in that direction, but we're not quite there yet. But I think the technology stack for training an artificial governor is starting to materialize. And people are now having the idea, I think Stripe is building one of these, they're having the idea that instead of just building a language foundation model, so an LLM, you can build foundation models for other things, right? So you can build a physics foundation model. Stripe is building a payments foundation model. Why would you want a payments foundation model? What would that do? Well, basically what they do is they take, so when Stripe sees a transaction, right?
Mm-hmm.
Typically that transaction is like some kind of vector in a big space. So, there's like representations of who the merchant is and who the customer is and what the payment method is and what the time was and the location and the device that was used and so on and so on and so on. And basically they use these vectors to train simpler machine learning algorithms to detect fraud, right? So when people are doing credit card fraud, um, credit cards work in a very silly way, right? If you know somebody's credit card number, you can basically spend their money, which is completely bonkers, right? Um, but basically, the old-fashioned traditional finance system is very insecure, right? It's insecure by design. Just knowing somebody's credit card number is enough to spend their money. But the way they prevent this all from collapsing is they have a lot of authority to block transactions, so it's not trustless. And when somebody does try to take advantage of the system, typically they'll do so not just once but many times, so they'll then start to form a pattern. So Stripe uses machine learning models to detect the patterns that correspond to fraud and find those patterns in this massive haystack of all these transactions. So what they actually have apparently done, again, I heard about this in a podcast, so I'm not sure how accurate this is. They actually built a foundation model where the model sees like billions or trillions of examples of transactions in an unsupervised fashion, just like training a language model on billions of sentences. And then once they've got this transactions foundation model pre-trained, then they can do a little bit of like, fine-tuning and reinforcement learning on it to teach it various tasks. Like, here's the task where you spot people doing credit card testing. Here's the task where you spot chargeback fraud. Here's the task where you try and spot which customers should be given special offers to try and retain them. Here's the task where you try and predict which customer is going to spend the most money. So there's like a whole bunch of these different machine learning tasks that you might want to perform. And they said, instead of just performing them all separately, why don't we train a single model the same way people trained a language model, a large language model, and then we'll get this huge model that knows a lot about the sort of geography and sort of types of transactions and
The vector space.
this big, sort of understand, it kind of can see the matrix, right? Like it can sort of see like what's going on. And then once you've got this, we'll just sort of train it to do each specific task. And apparently they're getting some value out of that. They're large enough in scale that it's worth it for them to do that. So I think we will see people start to train special purpose foundation models for different purposes. And I think somebody will eventually come up with a governance foundation model. And that is how we will get to governance by AI. I don't think the language models are ready for it. I think you have to train a governance foundation model.
On data that we have currently available, or do you think it will take a whole new kind of ingest to get the representative data for that model?
I don't know. I mean, it's hard for me to say. A lot of questions in machine learning are quite empirical, right? Either it works or it doesn't. You have to try it, and it's pointless to speculate until you do try it. My suspicion with governance is because governance is about counterfactuals, you're going to have to use effectively these sort of board game type simulations to actually get this thing to do sensible stuff. So I think your governance foundation model is going to have to spend a lot of time in relatively detailed simulations that we build. And those simulations themselves are going to have to be probably constructed in a semi-automated way in order to keep them maximally faithful to what actually happens in reality. Because if you train your governance foundation model against, only SimCity 2000, right, it's probably not going to have a sufficiently accurate picture of how the real world works. Maybe it'll have like some ideas that are not completely bonkers, but it's gonna, I think, computer games like Civilization and SimCity are not quite accurate enough. They're too artistic, they're too gamified, they're too arcadified. I think you're going to have to go back to something that's a lot more nerdy and less, it's not going to be about the graphics. It's going to be about just having a very complex model of the whole of society, of the people, of the infrastructure, of markets, and so on. So I think it'll probably look more like a big econometrics model than like a SimCity 2000 game. But I think it'll be something in between the two. I think that's how you will eventually get a foundation model that's good at governance. I think you probably also need to expose it to real data. Probably lagged, right? Time lagged real data. So, you record a bunch of real data about things like, the state of the economy, recorded crimes, markets, political events, all of this stuff, newspaper headlines. So you sort of record all of this visible stuff, and then you lag it by about 6 months, and you sort of present the model with, okay, this is all the data that we actually observed up to 6 months ago. Now I want you to predict what's going to happen in the next 6 months. And if you lag it by about 6 months, because you actually have the next 6 months data already, that's just the 6 months that have happened up to that point in time, you can quickly iterate. So the model gets it wrong, you're like, okay, tweak that, does a little bit worse, tweak it in the other direction, does a little bit better. So lagged real data may be good for training this stuff, but I think it's gonna be challenging to really arrange all of that stuff and make sure that what you're simulating and the reality are actually sufficiently similar in how that, in terms of process, that your simulations are not hurting it rather than helping it. Because the other thing you could do is you could say, we're not going to run any simulations. We're only going to train it on lagged data, right? And I suspect that won't work because most likely there's just too much hidden stuff. There's too much hidden mechanics going on for it to build good counterfactual models, right? That's one thing that real data is bad at doing, is counterfactuals, right? Because when something happens, you only get one thing that happens, right? Either you do invade Iraq or you don't. We don't get to see what happened in the alternate reality where, George W. Bush decided that he didn't want to do the war on terror. We have no idea what that world looks like, and that is a huge problem. Because if you don't know what the counterfactual worlds look like, if you have no idea what they look like, you're probably never actually going to learn anything about governance. So you have to have some way of peering into those counterfactuals, and the simulations is one way of doing it. There are also some cases of natural experiments where you have one policy and then something suddenly changes that people weren't expecting. So COVID created a lot of natural experiments, for example, because it was an unexpected change to the world. But natural experiments and simulations are probably two ways that you can peer into counterfactuals. So basically, I do think we are going to end up creating large governance models, but I think the technology is not quite there yet.
That's fascinating. Thank you so much for diving into that. There's two, I want to be respectful of your time. You've been so generous already. There are two ways I could figure us closing out. One would be to dive into that simulation problems more, because it's not only the curation of specific data that's a hurdle for those models, it's also the kind of recursive moment itself. When the model has to start dealing with its own existence, that seems to greatly amplify the problems of simulation. For example, with the prediction markets, we're now seeing them being gamed by inside information. There's obviously people who, once they realize, oh, I can make money off of predicting this, I also have this outcome under my control, now the prediction market is starting to fail because those insiders are taking advantage of it in some way.
Yeah, so I think this recursion aspect is something that simulations will be particularly good at, because you can simulate a world which has a simulator in it. That's not a problem.
Yes.
And you can find the fixed point of like conditional on there being a simulator that's making recommendations and people who are then either resisting them or accepting them. What's the and then the simulator has to take that into account, right? What's the fixed point of that process? So you can get that in a simulation quite easily, because the idea of these sort of governance simulations is they'll be relatively cheap. You could run, a million of these every day, right? So you'd find out what the fixed points actually were and what the distributions of outcomes actually were. But if you're only relying on historical data, you're never going to get that insight. So this is one reason why I think simulations have a role to play in simulated governance.
Does that somewhat break the trust aspect, though? Because I feel like we see this in politics already, is that sometimes politicians say things to produce an outcome, even though that thing in of itself is not true. Like Saddam Hussein has weapons of mass destruction. That's a lie that was told to get us into Iraq. But then you see them kind of retroactively come up with explanations for the lie itself. Condoleezza Rice is still going to insist that that was a valid move. So is there a trust problem there then that's insurmountable? Are the models going to have to lie to us to get us to the right outcome?
Yeah, that's a good question. There may be certain situations where, your model would say, if I told people the truth, they would do the wrong thing, so I'm going to lie to them. But maybe you would have a sort of logging feature where all of this has to be logged and it's automatically, unredacted after a certain amount of time.
I like
you
that
can
time gating. That seems like
you can
a
use
huge
that
deal.
time gating to sort of somewhat solve these kinds of issues. But ideally, in the ideal world, you would have governance that worked without lying, or at least without sort of explicit, lies. Maybe you could have lies of omission. Maybe you could have like, look, I know this thing, which if people knew would cause huge problems. So I'm just not going to tell them, and I'm going to put it in the classified file to be revealed in the year 2200 or something. So you could have that. And there's probably going to have to be things like that, right? There are almost certainly some things which it's better if people don't know. There are some simple examples like suicides, for example. They tend to be suicides are kind of a contagious disease. If you report about a suicide on the news, you tend to cause suicides, because there's the way people's brains work. A small subset of people are going to be susceptible to that kind of meme, and if they just don't know about it, they're going to be fine. They'll get over it and go and live a happy life. But if you just tell them that somebody else committed suicide, they'll be like, oh, suicide, that sounds good, and they'll go and kill themselves. So suicide is a bit of a contagious disease. I can see that there might be certain things that are like that, where it's simply better if you just don't mention it, if you don't tell people.
Yeah, it's scary. On the other point I wanted to get your take on, it seems like building the AI governance into an entrenched system, it also poses some more risks. However, on a newly created ICEstead environment, where you could not only run out a bunch of different experiments in parallel, but also collect an insane amount of data, because you could build that data collection infrastructure in from the ground up. That'd be a perfect testing ground. Have you thought about how AI governance would fit in there?
I think, so I've had this idea of colonizing either icebergs or artificially constructed ice vessels. The reason that you might want to do this is because ice is relatively cheap construction material if you're out in the sea. You can probably make a ton of ice for a couple of dollars. A ton of concrete probably costs a couple of $100, maybe $100. So you can be 50 times cheaper per ton, with the disadvantage that it has worse material properties. You can add sawdust or some kind of farm waste like rice husks into the ice at, again, a relatively cheap price, in order to improve its material properties. And you can insulate it so that it doesn't melt. Because if you have something that's relatively big, it's relatively easy to insulate.
It's a very well thought out idea. It sounds out there, but
it's
the
pretty
work
out
is
there. It's
serious.
pretty out there. I think it's not completely crazy. But
No.
having investigated it a little bit, one thing I've realized is that if you're going to build an ocean colony, it's probably going to be simpler and safer to build it out of concrete or seacrete. But it's going to be about between 4 and 10 times more expensive. So, you might be able to build a square kilometer worth of ice for, a couple of $1 billion, but a square kilometer of concrete, is going to be, maybe like 100 billion, right?
Yeah.
Or, 80 billion or 50 billion or something like that. So that might sound like a lot, but it's not actually that much. A single skyscraper, like a mid to high size skyscraper with maybe 80 stories high, that's probably going to cost you $1 billion to build on land, right? So infrastructure is already kind of expensive, and the cost of building it at sea, once you start to get big, isn't actually that much more. So I think sea colonies do have some kind of viability. I think to begin with, you would probably go with concrete-based sea colonies. And even before you do that, you can just build a cruise liner that people live on permanently. And people have already done that. That already exists. So I can't remember what it's called. I think there's been more than one of these projects where you just buy a ticket on this cruise liner. It's like a permanent cruise.
Yeah.
So you just literally buy effectively an apartment on a cruise liner. Now, if you go so ships are made out of steel, not concrete. But in World War II, the Americans actually did build quite a lot of concrete ships. Why? Because there was a steel shortage, because it was the war. The steel was for tanks, right? They didn't really want to build the ships out of steel if they didn't have to, right? So why not build all ships out of concrete? Are they more expensive? Well, no, it turns out they're not. For a given size ship, the cost of building it out of steel versus concrete is about the same. But the concrete version is significantly heavier. So for a given amount of buoyancy, it can carry less cargo. And it's probably a little bit slower as well because it's heavier, right? Heavier ships are a little bit slower. They're more under the water, so they've got a little bit more drag and more inertia. So they're a little more expensive to run around. So basically, because the overall transport efficiency of concrete ships was about 2 times worse than steel ships. So if you want to carry a certain amount of tonnage, like 100,000 tons, right, you might do that in one steel ship, but you need 2 concrete ships with the same size to carry the same tonnage. And because most of the costs of shipping are the crew and the fuel and the opportunity cost of the cargo, that meant that concrete ships never really took off. But the advantage of concrete ships over steel ships is a steel ship will basically rust in about a decade, whereas a concrete ship, it can kind of last pretty much forever.
Wow.
But it doesn't make sense if you're moving cargo from continent to continent and you need to carry a lot of cargo and go quickly. It doesn't make sense to pay for that extra longevity, right? But if you're building like a colony that's going to be there forever, it actually flips around, and you're quite happy for it to be twice as heavy because you don't care about that because it's not moving, right? If it lasts forever rather than lasting like a decade. Because obviously it only lasts a decade. Nobody's going to want to invest in it. Nobody's going to want to put permanent roots down there because it's going to be gone in 1 or 2 decades, right? But with oil platforms are mostly made of steel because once the oil is extracted, there's no reason for it to exist anymore. So it's fine if that oil platform only lasts a decade or 2. But if it's a floating city, that's not okay. You want it to last for 1,000 years. So you want to build it out of concrete or seacrete or something like that. And over time, the technology for concrete sea colonies has gotten significantly better. One of the weaknesses of concrete ships from the World War II era is they have steel rebar. So concrete needs rebar inside it because concrete is weak under tension. Steel is strong under tension. Concrete is cheap and strong under compression, but weak under tension. So you need a rebar inside it. But nowadays we actually have basalt rebar. So you use this special basalt. You make these basalt fibers basically, which is like kind of volcanic rock. That's what basalt is. And you can draw it out into these fibers, and they're incredibly strong in tension, just like steel. So you use these basalt fiber rebar, and because they're made out of stone basically, or basalt, they don't rust. It's impossible for them to rust.
Yeah.
It's chemically not possible. So basalt reinforced secrete will basically last forever in the ocean. But you will have to pay. So however big your floating city is, you're gonna have to pay for that much basalt and secrete and the labor to construct it. So it's going to be relatively expensive. But I think as we become richer because of AI and robotics and potentially technologies such as nuclear fission, so a lot of the cost of concrete is actually just like energy input cost. If we really got serious about nuclear power and we deregulated it, we got rid of the silly regulations that make nuclear expensive, that alone would probably flip, concrete or secret sea colonies, basalt, with basalt reinforcement into being viable. If you would, in addition, add in robotic labor to put it together and automated factories, that's really going to heavily flip the scale towards concrete sea colonies being viable.
Wow.
So I think there's a lot to be said for the concrete or secrete, which is similar to concrete, it's just a bit of a different chemistry, so it's more robust, right? So this sort of concrete type sea colonies, I think, are quite close to viability, if not already viable, but nobody's actually done it yet, right? It's just that they also have a scale problem. So if you have a small sea colony, nobody's going to want to be there. Now, the way that these cruise ships solve that is, instead of a cruise ship just plonking itself down in the ocean and saying, okay, buy an apartment, you can live there forever, they travel around the world, right? So because it's traveling around the world and it goes to all of these different destinations where you can get off and you can walk around the destination for a bit and then you go back into your apartment and it travels somewhere else,
Yeah.
that is now exciting and interesting for people, even if it's small. But if the thing is stationary, you need to make it big. You need to have about 50,000 people there and several square kilometers worth of land for people to want to permanently live on this floating platform. So anything smaller than that in scale, and it fundamentally doesn't work. So there's a scale problem. Because it has to be several square kilometers and stationary and big and have a lot of people, you need a pretty sizable investment to get it built. So if you're building with concrete, I personally think you're looking at tens of billions of dollars before you hit viability. So somebody has to invest tens of billions of dollars into one of the most insanely risky things that's ever happened in order for this to work. And that potential, that barrier, that scale barrier is why this hasn't happened yet. Right?
Yeah.
It's kind of like with Sam at the beginning. I was talking about Sam Altman and the LLMs. The reason that it took someone like Sam Altman to do it was because you had to invest tens of millions of dollars in both salaries and compute time into this sort of quixotic quest for artificial intelligence that a lot of people had concluded in the 20th century was basically impossible, and that it was like this nerd's dream, rapture of the nerds, never going to happen. What are you even smoking? And worse than that, they didn't even know what these models were going to be capable of, right? They sort of hypothesized that maybe they might have some capabilities, right? But they had no proof of it, right? So there
Yeah.
really was an essential step into the dark that had to be made there. And it could only really have happened in Silicon Valley, because nowhere else would have the risk appetite and the venture capital scene to actually do that kind of thing. But
Mm.
I think sort of sea colonies have a similar dynamic, where a sea colony kind of sounds crazy. People have been talking about seasteading forever, but it's never actually come to fruition. Seems kind of like this kind of quixotic, sort of silly quests, rapture of the libertarians instead of rapture of the nerds, right? So somebody has to have the balls to raise, a significant amount of capital and sink it into one of these things, and risk it and hope that 50,000 people will turn up and even pay them. Like, even at the beginning, you probably want to pay people to turn up, right? You want to have some kind of scheme that goes out into the world and finds the people who have the combination of being relatively poor but relatively high quality human capital. So maybe
Mm.
they're from Europe or Ukraine or even England or something, right? Where there are relatively high quality people who are being paid absolute peanuts. And so, there are certain people in certain situations where if you gave them a $10,000 a year scholarship or stipend to come to the sea colony, and you give them, their apartment for free, basically, and you say, just do this job, you can be like a receptionist, or you can I don't know, whatever. We've got some job for you as well, and on top
Yeah.
of your pay, there's a stipend. There's people who would do it. So and you might think, oh, that's going to be really expensive, but I mean, if you only have to do it for the first 1,000 people, right? $10,000 times 1,000 people is only $10 million. It's actually peanuts compared to what you paid to build this thing. So, even if you do it for all 50,000 people, you're paying them all $10,000 a year to be there, just to like get the place kind of seeded with some people. It's like totally worth it when you think about the costs. So you may have to pay people to be there in the first place. You have to be quite selective about that. Balaji Srinivasan has been running his network state conference, which I
Yes.
didn't attend, but I attended the last one. And basically, he's having some success in Singapore or near Singapore in Forest City. I don't think he's quite achieved takeoff of his network state yet, but he's kind of getting close, right? So that I think is going to be the model, right? You have a bunch of young people who are ambitious, and you always kind of think about it as like a floating university. That's kind of the
Yeah.
closest thing to what he's doing. So you invite young people who are ambitious and adventurous and still have their whole lives ahead of them, and you say, "Come to this seastead. We'll pay you to be there. We're doing a lot of cool things. There's a lot of cool people there." Um, I think that's how you get the social takeoff, and then I think the physical stuff is somebody has to actually, cough up, right? Somebody has to cough up. And not only do they have to cough up, there has to be somebody who's a competent executor who's actually going to execute on this stuff and not waste the money, which is a significant blockage on some of these
Yes.
things. But I think it's doable. I think concrete based colonies are a thing. And I think the advantage of an ice based system is you may be able to basically cut the capital requirements by a factor of 10, at the risk of having to take more risk earlier on when you prototype this stuff. Because it's not
Mm.
completely clear to me that an ice-based system would actually work, but it's also not completely clear that it wouldn't. So I
Mm.
think if somebody can come up with, 10, 20 million pounds or $20 million to do small scale tests, I think you could basically prove it one way or another. And then if it does work out, um, you could scale it up, and then instead of spending $50 billion for your sea colony, you only have to spend $2 billion, and that's a pretty big win.
Well, forgive me for bringing it up in that fashion. I just finished
Mm.
watching your interview with Anatoly Karlin regarding the
Yeah.
concept, and I'll link
Hmm.
that in here because you guys go in depth and you really
Yeah.
flesh out not only the feasibility, but the attractiveness of the entire concept. Two things that occurred to me while I was listening to that and your summation of it there is one, if you don't have the cruise ship ability to travel port to port, could you perhaps gain and lessen the network requirements by creating an attraction of some kind, by having a smaller permanent user or indwelling base, but
Hmm.
then having people come to it as part
Oh
of some
yeah.
kind of entertainment hub or something like that.
Oh yeah. You can have that. Yeah. I think in reality, like a lot of the problem. So I haven't been to any of these network states. Well, I've been to Zuzulu, but that was temporary. A lot of the problem these places have is that there's a lot of things that are bad about being small, right?
Yeah.
So I need a children's creche, I need a hospital, I need this, I need that. And all of these things are just fixed costs, right? So typically, when you look at the formation of cities, you see the intersection of two graphs. You have a
Mm.
graph, so you have the population on the x axis, and then you have your cost per capita, and you have your sort of revenue per capita, right? And basically, when those two cross, right, when the revenue per capita exceeds the cost per capita, you get a city or a village or whatever. But before they cross, it's just not viable. And if you try and start one, it will dissolve itself, it will fizzle away. Or at the very least, you'll need some kind of subsidy in order
Yeah.
to maintain it. So one example of this is the Antarctic colonies that America maintains. Those
Mm.
are basically subsidized, right?
Yeah.
If there wasn't a subsidy going into the Antarctic bases, they would cease to exist. But then you have like towns in Alaska. Like there's one town where the entire town lives in the same building, I think. Like it's this massive, massive tower block that's like 6 stories tall and about 200 yards long and 100 yards wide. I can't remember what it's called.
Jesus.
But
Yeah.
the whole town is in that one building, right? Why? Well, because it's Alaska, it's cold, right? So by being in the same building, they all share the same heat and the same amenities. And if you want to go to the shop, you don't have to go outside because the shop is in the building, right? If you want to go to school, you don't have to go outside. The school is in the building, right? So that is not, as far as I'm aware, subsidized, right?
Mm-hmm.
So there's a crossover point somewhere where basically small colonies can persist, right? If the population is large enough such that the per capita revenue exceeds the per capita infrastructure costs.
Mm.
So basically, you have to exceed a certain threshold population such that because basically infrastructure costs have diminishing per capita costs, right?
Mm.
If you go from 10 people to 100 to 1,000, every time you multiply the population by 10, the amount that each person has to pay for these costs will typically decrease. Maybe not quite by a whole factor of 10, but like, so like if there's 1,000 people and you need a police station, right? Each person pays 1/1000th of a police station that can serve 1,000. But if there's
Yeah.
10 people and you need a police station, well, a police station that serves 10 is not 100 times cheaper than a police station that serves 1,000. It's maybe only 2 or 3 times cheaper, right?
Mm.
So then, in the case of the village of 10 people, they're paying 30 times more for their police station, right? So that village probably won't have a police station, right? The little, not really a village, like a little hamlet, a little collection of 10 people is just too expensive, right, to have its
Yeah.
own police station. But there's a certain size of community where it becomes viable, where the per capita infrastructure cost is small enough. And also, at the same time, per capita revenue tends to be super linear. If you have a village of 10, and then 100, and then 1,000, and then 10,000, 100,000, and 1,000,000 people, once you get to a city of 1,000,000 people, the amount each person is going to be earning in, or maybe not wages, but certainly the value they generate, the GDP per person in that city of 1,000,000,
Mm.
all else equal, is going to be a lot higher than if they were in a hamlet of 10 people. Why? Well, because like industries have gains from scale, right? There are agglomerative gains, right? If you have only 10 people or maybe only 100 people, you could still have a software company in a village of 100 people, but every single person who lived in that village would have to work for that software company. And if they wanted to hire somebody new, or if they need to fire somebody and replace them, then we should out of luck. There wouldn't be anybody. But if there's a city of 1,000,000 people and you have a software company there and you need to hire one new person, well, you have this massive pool of labor. You have all of these people, and there's all sorts of other companies. And maybe there's somebody from a different company who just quit that because it wasn't right for him, and he'd come work at your company, and all of this good stuff can happen as a result of
Yeah.
agglomerative gains. So these kinds of sort of exotic towns and settlements and colonies and stuff, they all get better as they get bigger. And that is
Network effects.
basically why it's hard for them to exist,
Mm.
because there's a sort of threshold scale that they have to exceed. And I think for sea colonies, it's about 50,000 people.
Mm.
Once you exceed 50,000 people, you can be self-sustaining based upon the labor output of those people. So you can have a sea colony where you don't even manufacture anything. All you have is software businesses and biotech and financial services and so on. And obviously some retirees and some children and some local service economy stuff, right? All of
Yeah.
that can be self-sustaining above about 50,000 people.
Yeah.
Maybe a bit more, maybe a bit less. Maybe it's 100,000, maybe it's 20,000, but it's that kind of order of magnitude that you need to hit to become sustainable or self-sustaining as a settlement.
Hmm.
But if you need that many people, it needs to be really big. And that means it needs a lot of money to build it. And that means it's taking a lot of risk. And so investors are scared and they don't want to do it. But I think, as the world gets richer, relative to the total amount of money in the world, that fixed scale gets smaller and smaller and smaller and smaller over time, and that line eventually intersects with the line of what people are actually prepared to risk, or how much money the richest seasteading billionaire has to blow on this keeps going up over time, and of course technology keeps decreasing the cost. So this is why I think this kind of like oceanic colony-based seasteading is actually inevitable, and it's just a
Hmm.
question of time, and we may be on the cusp of this thing, kind of like in 2015, we were kind of on the cusp of LLMs. The lines are about to cross.
There is a fascinating intersection there too. I was thinking about what kind of natural production might these kind of ice steading or seasteading concrete structures produce. When we were talking about AI governance,
Yeah.
could they not be a test bed for that kind of thing? And could the data they generate from monitoring, from collecting the data of the inhabitants, be used to subsidize the cost of the island itself?
It's possible, but I think just producing that data is cheaper onshore, right? If you really need to monitor a bunch of people for a governance model, it's much easier to go to a random town in Kansas and say, "Hey, everyone, we'll pay you $500 a month to have like cameras and microphones everywhere."
Yeah.
And there's going to be some place in maybe like Arkansas or the Appalachian Mountains or somewhere that's going to be like, "Hell yes, we're all poor. Just come and surveil the fuck out of us," right?
Yeah, just not what they do with the
DeWilt,
donkeys in the barn. Yeah.
exactly, yeah. Right, yeah, right. But like, just yeah, they will absolutely take you up on that. So, and that's not actually that much money if you're surveilling 10,000 people for a year and you're paying them like $1,000 each, right? I mean, again, it's like $10 million or something. So it's like totally like that's a very small amount of money in comparison to just the cost of even prototyping the technology, never mind actually building it, right? Like $10 million isn't even that much money. That's like kind of seed round funding for this, really, right? Is 10 million is what you spend to have like a CEO and like 3 or 4 good technical people
Yeah.
and the overheads and the equipment they need. That's $10
Yeah.
million over, say, a couple of years, right?
No, that makes sense.
So it's not much money. So I think, but I do think I'll tell you what I think these seasteads would produce. Basically, tax evasion. Like basically that is the thing that you cannot generate on land. Because if you're on land, you're under the jurisdiction of the government, and the government wants to steal your money. And in fact, in Britain and in Europe, the governments are stealing almost all of your money, right? It's outrageous. The true amount that they're stealing is horrendous. It's not just the tax. There's like various stealth taxes, there's consumption taxes, there's implicit taxes by overpricing rent, and there's electricity taxes that have made electricity in the UK 5 times more expensive than in the rest of the world. I mean, people are paying like maybe like $2,000 a year on their electricity bill, and the average salary here is about $40,000.
It's insane.
Right? That's a lot of money.
Yeah.
So, the thing that you can't produce on land is tax evasion, effectively, or not just tax evasion, but freedom of all forms, right? Especially freedom from being taxed to oblivion by your own government. So I think the point at which this really takes off is the point when the technology is de-risked enough so that you can go to a country like England or Germany and you can find 100,000 English people or 100,000 Germans who are all at least middle class and they're all employed. So you don't really want like people in care homes and stuff like that because they're more a financial drag. But you want 100,000 people who are middle class, at least relatively intelligent, employed, and productive, and getting taxed effectively 90% by the governments in Europe. And then you say to them, "Come to my magical mystery island," right? Okay. And you can do whatever job you were doing in Belgium or Germany or Holland or France, but no taxes or minimal taxes, no diversity, no wokeness, so these things will attract people, I think. And once you get to that scale of, say, 50 to 100,000 people, right? If you're taking, say, effectively you're somehow taking 10% of that. So instead of taxing people 90%, you're taxing them about 10%. That's a great deal for people. But even 10%, if you have 100,000 people who are each producing, say $100,000 in value, which is not that hard, right? So maybe people aren't getting paid $100,000, but people generally produce more value than they're paid. I mean, otherwise, why would you employ them, right?
Yeah.
So it's not that hard for somebody to produce $100,000 a year in value. So if you have 100,000 people each producing $100,000, well, when you do the math on that, that's 10 to the 5 times 10 to the 5 is 10 to the 10, which is $10 billion. $10 billion, right? So if you take 10% of that, you have a tax revenue of $1 billion per year. And if you amortize the construction cost over 30 years, that's, maybe 20 or $30 billion to construct this thing is totally feasible, right?
Yeah.
So I think it's
Self-sustaining.
almost like financially kind of viable already, but the investment, the risk, the technical, the combination of technical and political risk to actually make this happen means it's quite hard.
Yeah.
But I do think it's viable. I do think you can get, and the thing is, as we get into the AI age, what's going to happen is governments are not just going to want to tax people, they're also going to want to tax the AIs, right? So if there's some kind of digital product that you want to make, software or scientific knowledge or medical technology, or even some kind of like concentrated high value physical product, maybe you're making drones or robots, or maybe you're making nano machines or something like that, right? Like anything, right? Anything that you're making that's relatively high value per person, right? So you can't have people doing like low value labor. The economics doesn't add up. You can't have industries that require a lot of raw materials, because you're not going to have the raw material. You're not going to have most raw materials. You are going to have some raw materials, because there's actually a lot of raw materials in the seawater that you can extract, but it's like a limited subset. So magnesium, for example, you can actually mass manufacture a lot of magnesium, and magnesium is, because there's loads of magnesium in seawater. In fact, in America, they used to mass produce magnesium by purifying seawater, right, or extracting the magnesium. So magnesium is actually going to be quite an important element, because it's useful for electric cars, or for any kind of car, really. You can make the car body out of magnesium. So there's certain additives you can put in the magnesium to stop it from, because like normal magnesium, if you can actually burn it, it burns. But there's certain additives you can put in them now, they've discovered, that stop it from being flammable, and make it stronger. And because it's one of the lightest metals, it's very light and very strong. So magnesium is sort of to aluminium as aluminium is to steel. So it's lighter and it's lighter, and per kilogram it's stronger. So magnesium aircraft, magnesium drones, magnesium cars. So you could have a magnesium-based physical manufacturing system on a seastead, but I suspect that probably won't come for a while. I suspect that it will be knowledge and information economies that just want to avoid all of the taxes that come with legacy governments. So that, I think, is what you could do with a sort of ocean-based seastead type colony. And I think we probably are viable, but the risk is insanely high, and the returns at the moment don't look as juicy as returns on pouring more money into AI models. But I think we're rapidly approaching the diminishing returns point where AI is kind of a little bit sort of done. And then maybe some of the money will want to look for other things, and one of those things might be sea colonies.
That is so fascinating. Roko, I can't thank you enough for all the nuclear information bombs that you have dropped on me. I'm going to be processing this for so long.
Right.
I know you mentioned having something potentially to tease. Is there any hints or vague suggestions you want to throw out there for what's coming up for your future work?
Well, I mean, probably nothing beyond what I've already said.
God bless.
Basically, right now I'm focused on. I've recently had to make an international move, so I've been moving house and dealing with sort of that kind of thing. I'm not particularly settled at the moment. I've just moved into a new flat, so I'm busy doing kind of personal type stuff. But let's hope that's all done relatively soon, and I can come out with some interesting things for people to see.
I can't wait to see it. Like I said, you were the genesis in many ways of my engagement with AI, and I have no doubt that there's going to be much more down the road. So happy to have you here anytime, but thank you so much for your time here today.
Appreciate it.